Well, we're beginning the fixed income series now. Not a lot of readings here. We can get through this rather quickly. It may be a little thick in the reading at times, but in my opinion, it's unnecessarily thick. The concepts that we're going to be doing are actually so very straightforward. So I hope to prove that to you as we go on. I'm going to take some time with the first 3 or 4 learning objectives, because I find that if I lay that out nicely, if I lay that out really well, everything builds off of that. So as long as you see the connections, then that's great. What trips people up a lot of times is the terminology and the notation. That if you understand the terminology, that when I say spot rate in your mind, you see exactly what that is. And when you look at the notation, and the notation can get pretty ugly. If you get the notation, really, the concepts in this chapter are quite simple. So let's go ahead and look at our 2 big words we're going to be dealing with for a while, the spot rate and the forward rate. A spot rate is a rate of interest on a security that makes a single payment at a future point in time. Well, that's a zero coupon bond, right? You get one payment at one future point in time. Let's be clear what the spot rate is. It is for government securities. Here we're talking about government securities. The idea that they must be default risk-free defines what spot rates are. A forward rate is an interest rate that we'll agree on today that won't take effect until some future period. I think that's fairly straightforward. So let's just have a look at really what we're talking about here with the spot rate. The R right here in this formula, that's our spot rate. So we can conceive of a dollar that we'll be receiving at time t. This $1 we call a single unit payment, and we'll be using $1 to represent all our zero coupon bonds from now on. It matures at par, so it matures at $1. What do we know about zero coupon bonds? We know they're all sold at a discount. So when we calculate the present value, we'll actually just call that a discount factor now as opposed to present value. And it's $1, our $1 payment, discounted back to today. And again, that R, let's stress that is a default risk-free rate, which means we are talking about government securities here. So if I want to say what I just said a little more formally, I can say it along the lines of this equation, that the price that we would pay for a zero coupon bond that matures at time t can be expressed with this function, 1 divided by 1 plus whatever rate of return is required to the power of t. So that's just discounting back to today. The interest rate that we're using down here will be the zero coupon bonds yield to maturity. And as long as this is a treasury bill or a treasury note, it is also called a spot rate. The price that we get to, recall on the previous screen, I said we'll refer to that as a discount factor. So that if we have a list of all the different time periods, time period 1, 2, 3, all the way to as far as we want to go, and we have discount factors for all of them, we can determine what the spot rates are on all of them. So we can look at observed market prices for a zero coupon bond maturing at period 1, period 2, period 3, etc. From that, we can derive a spot rate. If, on the other hand, we have spot rates, we can derive the discount factors or the prices. This set is called a discount function, and if you remember your high school math, you know that a function specifies a mapping from one variable to another. Well, we can go from the discount factor to the spot price, or we can go from the discount factor to the spot rate, or from the spot rate to the discount factor. Once we have our spot rates, we can draw them out on a graph. We can plot our rates here and our time periods here, and this, if we're plotting if these are the spot rates that we arrive at, is called a spot yield curve or a spot curve. So having introduced one of the heroes of our story, the spot curve, let's look at some of the characteristics of this fellow. Each point on the spot curve represents an annualized return on, and here are the characteristics that the zero coupon bond has to satisfy: option-free, default risk-free, and of course it's a zero coupon bond. So the default risk really brings it down to just treasuries, right? There is no reinvestment risk, simply because there are no coupons to receive, no reinvestment risk. Thus, the stated yield whatever the spot rate we arrive at, is the actual realized return if held to maturity. The yield on a zero maturing at T is regarded as the most accurate representation of the T-year interest rate. No reinvestment risk, hence we can arrive at that conclusion, the most accurate representation of the T-year interest rate. So, market forces, whatever market forces there are, whether there's bullish sentiment, bearish sentiment, risk on, risk off, whatever's going on, that will affect the market price of all bonds, including zeros, including treasuries. As the market price of these bonds move, the rate, the yields to maturity also move. Well, these yields to maturity are map out the spot curve, so we can see that the shape and the level of the spot curve are dynamic. By dynamic, we mean we don't just draw one line and say, there we are, we're good for the day. This thing changes. As prices change, the shape and the level of the yield curve change, and that change, those dynamics, have implications for how we would manage a portfolio of bonds. Okay, so on the screen I have a timeline here, and I'm going to use a lot of these because it really makes this chapter so easy when you can look at it in a timeline form as opposed to look at it in function form, with all the notation. So let's say that we have 6 spot rates, R1 through R6. So there's R1, R2, R3. Notice here's 1 period 0 to 1, so you can see how I've done this. 1, 2, 3, 4, 5, 6. We have 6 spot rates. I can calculate the discount factors from each of these spot rates. It's really easy to do. If the 1 period, R1 for instance, is 1%, so the discount factor is $1 discounted back for 1 year, 1.01 will give me 99.009. I can just go through each of them, and those are the discount factors I arrive at. So I think we get spot rates. I think that's easy enough. Where do we get our spot rates? Well, we can observe them. We just observe a bunch of zeros trading in the market, and whatever price they're trading at, whatever discount factor they have, we can figure out what the spot rate is. Given a spot curve, we can figure out what all the discount factors are. So great. As long as we have one or the other, we got it. And we know that we're dealing with government securities, with treasuries on this. Great. But here's a question. What if we want a rate beginning in year 2 for 2 years? So in other words, I want a rate that starts here, and I want this rate. Well, I have from time 0 to 1, I have from time 0 to 2, 0 to 3, 0 to 4, I have everything. And that's the idea behind spot, is spot means today. Well, what is this rate going to be? It turns out that if we have these spot rates, we can determine what this rate will be if we agree on it today. That will be a forward rate, and the spot prices will tell us what forward rate it implies. Hence it's referred to, sometimes you'll see it's referred to as an implied forward rate. So here we are formally. A forward rate is a rate determined today for a loan that will be initiated in a future time period. So this would be a loan that starts in year 2 for 2 years. So before we jump into all of the notation, I'm going to show you how absolutely simple it is to figure out a missing rate, some forward rate in the future. Let's say we can observe 2 spot rates. We observe the 2-year spot rate, which is 3%, and we observe the 3-year spot rate, which is 4%. Remember, these are expressed annually, right? So that's not 3% over the 2 years, it's 3% per year for 2 years. So we have a 3% and a 4%. To figure out this one, we just have to invoke the no arbitrage principle. And what this says is that tradable securities with identical cash flow payments must have the same price. So if our forward loan, if we invest at time 2, let's say that we buy a 0 coupon bond at time 2, it matures at time 3 at 1. If we use the spot rate and we buy a 3-year 0 coupon bond, it matures at time 1. We can discount this $1 back to period 2 and then discount that back to today. So since they both would have the same identical cash flows, they should have the same price. Well, we can also take that the other way. we can say that a dollar invested in either the top part of the line or in the bottom part of the line should end up with the same amount of money. And that's how we determine our missing variable here. So it's very simple. If we invest a dollar at the bottom of the line, what are we going to have? 1.04 over 3 years. That must equal what we can get at the top of the line, which is 1.03 for 2 years, multiplied by our missing variable here. And I'm just going to call it x. Okay? X, by the way, will stand in for 1 plus our forward rate when, in 2 years, what is it? A 1 year forward. Another way of saying it is I'm just looking for 1 plus r, whatever the r is. So I know that I have to remove 1. Instead of me writing all the terminology, I'm just going to put in x and solve for x. Just an unknown. So I'm going to get 1.124864 equals 1.0609x. X is easy algebraically to solve for at this point, 1.0602922. I know that x is 1 plus r, so to get my forward rate to 1, which is what I want up here, I just subtract 1, I get 6.02922%. So if I have a spot rate for the up to the period of time where my forward rate begins, and I have a spot rate that lasts to the period of time where my forward rate ends, I can figure out my forward rate. Nice and simple, right? So if we have spot rates or a spot curve, we can derive forward rates or the forward curve. We're going to see that we can go backwards on that too. It makes sense, right? If I got a series of spot rates, if I have a spot curve, I can get all of the forward rates. And the forward rates draw out a forward curve. And if I have a forward curve, clearly I can go backwards and find the spot rates. Because if I can start at spot and go to forward, I should be able to go from forward and go back to spot. We're going to see that a little later. So having introduced our second main character to the story, the forward rate, let's have a look at the characteristics of that. All the forward rates will draw out a forward curve. If our spot curve, by the way, is upward sloping, our forward curve will be upward sloping. Not only that, our forward curve will be above our spot curve. Those statements we're going to prove a little later on. It's just nice to have some clarity on where we're headed, right? So what do each one of these things mean? We know what a spot rate is for each of the time periods, but if I'm looking at one, I'm looking at that rate. What does that rate mean? That tells me when a loan is made. If it's made at time period 1, if the loan is going to be made at t equals 1, it will be for this rate. If the loan is made at t equals 2, that's the forward rate. If it's made at t equal 3, that's the forward rate. And each loan is for one period. We find each of these forward rates by looking for f t1, always 1. So we read this, by the way. I don't know if you're familiar with how to read this or get confused with this. An easy way to do it for the rate is to look at it in terms of when, what. And how I remember this is I can't look at the W's because, well, they're equal. I can't look at WH because they're equal, but I can look at the last letter. N comes before T, so I know I'm going to put it in the form of when, what. So here's how I read it. We are looking for a rate. When? In 2 years. For what? A 1 year term. There we go. So this is this would be F11, this would be F21, F31, F41, F on and on and on. So FT, whatever time period it is, for one period. That doesn't mean we can only calculate a forward rate for one period. We can easily take the spot curve and say, well, what would be the rate for a 2 year zero beginning in year 2? It's just we wouldn't plot that forward rate on the forward curve. The forward curve is just a series of one period forward rates. That's it. So is this very useful for anything other than figuring out the rate on 1 year terms? No. Let's say we wanted a 3 year loan starting at T2. So here's T2, and we want a 3 year loan. We want this. What would be the rate? Well, we can take the forward rate 1 plus R2 multiplied by 1 plus R3 multiplied by 1 plus R4 and just find the third root of it. This is just compounding and then finding the third root to figure out what the rate is. A constant rate, an annualized rate per year over those 3 years should equal $1 and or whatever. We'll say $1 invested at this rate, then reinvested at the next rate, then reinvested at the next rate should be equal to one rate that's the same all through. So we can figure it out. That's easy enough. So let's introduce some of the notation that the reading introduces, the T star and the T, and see what we're doing here. So here's our when and here's our what. So where our forward rate is always written as a little f, if we're looking at the rate, is lowercase f, T star T. When? In T star years. For what? For T years. Which means the full length of time from today to the end of that period of time is T star plus T. So the full rate is the full period of time will be T star plus T. The zero will not be purchased until T star, and the duration of the zero will be T years. So when we talk about a forward rate, we're using lowercase f T star T. When what? When we're talking about the price that we will pay, that's the rate. If we want the price or the discount factor, we use a capital F T star T. So we can buy a zero in T star years for T years that matures at $1. What is the rate and what is the price? This is the notation for the rate. This is the notation for the price. But how do I figure out the rate and how do I figure out the price for this forward contract? I've already shown you on the previous screen when we did that small little example how to figure out a forward, how to use the two spot rates to figure out what the forward rate would be. But let's, again, we want to get more formal. We want to express it in terms of T star and T to see what we get at. Well, of the rate and of the price, the forward rate and the forward price, let's focus right now on the price, the discount factor. So we're going to introduce something called a forward pricing model, and since we're dealing with price, we should have a capital F, and we do have a capital F here. This is our unknown. This is what we've got to figure out. And we have our price for a zero coupon bond that matures in T star plus T years. And we will have a price for a bond that matures, or a zero coupon bond that matures in T star years. And we just have to figure out, well, what is the discount factor on the forward contract, on the forward price. So let's say that our T is 2, our T star is 1, and we have a 1-year spot rate of 7% and a 3-year spot rate of 9%. What always helps me out is I just draw a little timeline and I say, okay, 0, 1, 2, 3, 0, 1, 2, 3. And what are we doing here? Well, I have a spot rate for 1 year, so I have this rate at 7%. I have a spot rate for 3 years, T star plus 3. I have this one here at 9%. This is my wild card, but I'm not looking for F. I'm looking for the discount factor, F, capital F. So that means I need to turn this into a discount factor and turn this into a discount factor. And all this formula is saying down here is that the discount factor associated with this zero coupon bond, T star plus T, if this is T star, if 1 is T star, we'll put a T star here, and if the period of time is T, 3 over here must be T star plus T. And is it? 2 plus 1 is 3 in this in our example. So there we go. So all we're saying is that the discount factor associated with this zero coupon bond must be equal to the discount factor associated with this zero coupon bond multiplied by the discount factor associated with this zero coupon bond. So we just need to solve for that. So what do we need? We need discount factors. Our discount factor for this 1 year zero coupon bond is simple. What do we get? What's our P1 going to be? Well, our payment we know is 1, and since R1, the spot rate is 7%, we discount that back by 1.07. That will give us 0.9346. And what is the discount factor for a zero coupon bond with these characteristics? Well, we need a P3. remember now, if we use the notation R3, we're specifically talking about the spot rate. P3 means we're talking about the discount factor. What's our payoff? 1, and we have to bring that back to today. Well, we're going to bring it back at 1.09 to the power of 3. That will give us 0.7722. So now all we have to do is just go back up here and have a look at our formula and just fill in the variables that we've come to. So what's our first one? P t star plus t. Our t star is 1, our t is 2, t star plus t is 3. So our P3 is 0.7722 equals our P t star. That's our P1 that we figured out, 0.9346. And we multiply that by x. And I'm going to let x stand in for this term here. And this term here is really our x is going to equal F12. What is 12? When? In 1 year. For what? A 2-year term. So let's continue on. We need our discount rate. So there's our x. So our x will equal 0.7722 over 0.9346, which gives us 0.8262. So there we go. That's nice and simple, right? In 1 year, we will pay 0.8262 for a 2-year zero coupon bond that has a payoff of $1. A note here. You can use F12. You can stick the full notation in F12 if that's if you find that smoother for you. I like to just substitute in x so I know what my wildcard is all the time, and then if x requires me to subtract 1 at some other point, when I'm looking at rates, it will require me to subtract 1. I just like putting in x because it's just faster. I don't have to write out all this stuff, especially on an exam if I'm writing it out. I want as many shortcuts as I can. I like to just put in x. I know what x stands in for. All right, we've done price. Let's do rate. I already did rate a little while ago as just an example to show you what this looks like, but we'll do it in formal notation now. And here's what it looks like. It looks pretty ugly, right? But this is really not saying much. What's t star plus t? Well, that's the full duration, the full term, right? So this is 1 plus the spot rate for a zero coupon bond that matures at that time to the power of how many periods that is, must equal 1 plus the r to or rt star to the power of t star. That's just the first period of time multiplied by, of course, the second period of time, and that would be the forward rate that we're looking at. So this is called a forward rate model. So let's have a look at what we're doing here. Let's say that this is t star. This is a period of time t, so this is t star plus t. So if you look at this formula up here, I'm sure you can find all of the sections that we need. Let's just use an example, and let's say that the spot rate from period 0 to t star, we'll let t star equal 1 is 3%. Again, this is a 2-year forward that we're looking for. It begins in 1 year for 2 years. And we have the 3-year spot rate, which is 4%. This obviously is t star plus t. So what do we, this couldn't be easier actually once you see it in this format. What is this first term here? It's 1 plus the spot rate for a 0 that matures at t star plus t, which is 3 years. That's a 4. So it's 1.04 to the power of t star plus t star plus t, which is 3, must equal 1.03, and this is only 1 period, times x squared. And again, notice here I'm saying let x equal this entire term. We're going to let x equal this entire term, but notice with no power, and this is to the power of t. Since it's for 2 years, we square it. And you just solve algebraically. So you can solve any of these forward rates by drawing out your timeline, and what you do is you identify the period of time on the top of your timeline, identify the period of time covered by either the forward rate or the forward price. Then from 0, at the top of the line, from 0 to the beginning of the forward rate, you're going to need a spot rate for that period of time. And on the bottom of the line, you need a spot rate for the full period of time. Then it's just the spot rate for the full period of time equals, you just multiply everything out, equate the sides, and off you go. So if you continue on with this, this is easy enough. You expand this, divide through by this, take the square root. You will get equals 1.045036. That will be x. X will equal that. But remember, I said let x equal this. So if you drop off the 1, F12 must equal 4.5036%. So once you can conceive of it in terms of this, and I like the timeline because it's just so easy to do. After you put the timeline in, we're going to do a number of problems where it may look challenging at first, but once we start drawing it out on the timeline, it's almost juvenile to calculate forward rates from spot rates. Okay, so let's make some statements here. When the spot curve is upward sloping, the forward curve will lie above the spot curve, which also means it has to be upward sloping as well, right? When the spot curve is downward sloping, the forward curve will lie below the spot curve. We'll revisit this a little later on. Let's get those points out right now. So let's look at an example of that. Let's look at an upward sloping spot curve. 1, 2, 3, 9%, 10%, 11. And again, to keep you online, what does this 9% mean? That is the spot rate for a 1-year treasury, or for a treasury that matures in 1 year. That's the discount rate, the yield to maturity, the spot rate, however you want to say it. So 9, 10, 11. So we have an upward sloping spot curve. So here's from 0 to 1, we have 9. From 0 to 2, it's 10. And from 0 to 3, it's 11. So I've just put our spot rates here. We have enough information now where we can calculate a forward rate for this period of time that begins in 1 year, that lasts for 1 year. And F21, that means it begins in 2 years and lasts for 1 year. We can calculate these two rates. So let's go ahead and do that. F11, what do we need to calculate F11? We need to fill in the top of the line and the bottom of the line. So we're going to need the 2-year spot and the 1-year spot to get the difference between these two. So the bottom of the line has to equal the top of the line. What's the bottom of the line? 1.1 squared must equal 1.09x. Again, I let x stand in for 1 plus, right? So if you solve for x, you will get 1.11009. You don't need me to solve that algebraically. You'll get 1.11009. Know that you have to subtract your r, so your F11 is 11.009%. Is it above the 10%? Yes, it is. Let's calculate F21. Well, for this one, we're going to need a 3-year spot, and since this only covers this period of time, we need the 2-year spot. So just imagine this one flipped to the top of the line. So what's on the bottom of the line? 1.11 to the power of 3 must equal 1.1 to the power of 2 times x. And we solve for x. And x will give us 1.130274. Knowing that my x is 1 plus, I take off the 1. My F21 is going to be 13.03. I'll round that up to 3. 13.03%. Is that above is that above my R3? It is. So you can see that the forward curve will be above the spot curve on an upward sloping spot curve. Here's a question. Given this timeline, how many spot rates do you think that I can calculate? Well, these two are simple enough. Is there another one that I can calculate? There certainly is. It's this one right here, which is F12. It's a 2-year spot rate, which is this one down here. So let's go ahead and do that. What do we need to calculate this? We need what's on top of the line, and we need the full bottom of the line. So what do we have on the bottom? 1.11 to the power of 3 equals, top of the line, 1.09 times x squared, because it's 2 periods now. And I just solve for x squared. You work your way down. I'll get to x equals 1.120137. I know that I'm dropping my 1 to get my F12 will equal 12.01, and we'll just shorten it to 4%. Is this rate above the highest rate I used? The highest rate I used was 11%. This is 12%. There you go. No matter how you do it, the forward rate will always be above the highest spot rate you use in getting to that forward rate. So let's look at another relationship between the spot rate for a particular period of time and the forward rates. And the curriculum gives you this big mess of stuff in the middle of a page. And all this is saying is that the forward rate for some period of time can be conceived of as a series, the spot rate for some future period of time can be conceived of a series of forward rates multiplied together. So we start with the 1 period spot rate and we'd multiply it by successive forward rates so that we can arrive at a spot rate for a maturity of t by taking the geometric mean of a spot rate for a security with maturity of t equals 1 and a series of t minus 1 forward rates. So as we've done throughout, things look better with an example. So let's look at an example. We have R1 and R2. We have two spot rates here and we have some forward rates. Let's see if we can derive R2 by using this particular formula here. So what we're saying for R2 is that it should equal 1 plus R1. R1 is 9, 1.09, multiplied by the next forward rate, F11. F11 is 11.1, so 1.1101. And that will be to the power of 1 over t. Since this is 2 periods, that's a 2. It'll be to the power of 1 over 2 minus 1. That's all that's saying, is that if we multiply the spot rate by the implied forward rate that we have, we should get the spot rate for the 2-year zero. And if you do the math on this, you will get 10%. You'll recall that we already knew what R3 was. So let's see what we get here with R3. In the examples that we have been using, you'll remember that R3 was 11%. So let's see if we get 11%. We start with the 1-year spot, or the 1 period spot, 1.09. Then we'll go to F11, then we'll use F21, and we'll multiply them in succession. 1.1101, 1.1303, and we are expected to take the 1 over 3, the third root of this, minus 1. And if you multiply this all out and you take the third root of it and subtract 1, you will get 11%. So this is an important relationship that we're going to use later on. It's just let's be aware that that relationship exists, as it must. As it must exist, because all of the forward rates are the rates we calculated as implied by the spot curve. So if the spot curve looks like this and we need a rate that starts at a particular period of time to here, we can figure it out from the spot rate. That's the big message here. What does it mean? How can we interpret that? What are we saying when we say that the forward rate is implied from the spot rate? We're saying that given the shape of the yield curve, that implies that the marketplace is pricing in what the future spot price will be in the forward rate. So if we have, for instance, our forward rate in 1 year is 11.01. Our current spot is 9%. If we go into the spot market today and buy a 1-year zero, we'll yield 9%. If we buy a 2-year zero today, we'll yield 10%. And if we buy a 3-year zero today, we'll yield 11%. What the market is implicitly saying by the shape of this curve, by the slope of this curve, what it's saying is that in a year from now, we expect the 1-year spot rate to be 11.01. We expect the 1-year forward rate at that point in time to be 13.03. In 2 years from now, we expect the 1-year spot rate to be 13.03. So we know on an upward sloping spot curve, the forward curve lies above the spot curve. What this is saying is that over time, we expect the spot curve to evolve and drift upwards to match what the forward curve looks like today. If we didn't expect that, we would expect a different shape for the spot curve, because traders would say we don't expect rates to look like this in the future, so some parts of the spot curve must change to reflect the fact that that's not going to be there. All right, this next two screens that I'm going to go through, I debated even putting them in because they don't add a lot of value. But they're there, and I thought, well, for the curious mind, they might want to see. I'm going to spend no more than another 45 seconds on this screen. I'm not going to really go through it a lot. What I want to do is clear up a problem with the book, and this is why I don't like the way this chapter is written. It's not accessible at all. It's thick, and it makes a lot of leaps. Anyways, the curriculum gives you the first derivation of this formula here. This is the forward rate model that we've already seen. Then it says it can also be expressed like this, and then it leaves it at that, and it just gives you this expression here. Well, if you're like me, and you see that, well, this can be expressed like this, I like to get out a sheet of paper and work through it and make sure that that is right, that I can see exactly how we get there, because I don't want to memorize this. If I have to remember this and I have to remember this, I got to remember two things. But if I have to remember this, I can get there. I don't have to remember this if I know how to get there. So here's how you get there. We have three terms here. We're going to isolate the third term on this side. So what we do is we take this term and we divide through. So that first step is rather easy to do. Then we want to get rid of the t over here by taking a root to the tth power. So all we do is, since we have power terms already, when you do something like this, you can just divide your power term by the power term that you're trying to take a root of. And since we have t star plus t over t, we can divide it into t star over t plus t over t, which is all I did here. And the denominator is t star over t. That gets rid of the t here and it places it here. But since we have t star over t plus t over t, well, that's a whole extra 1 unit. Let's just break that one out. So you'll notice that this term just gets broken out over here. And now we have t star over t in the numerator, t star over t in the denominator. We can isolate those outside, so we can just put brackets around that, isolate the power term outside. Here's the lonely guy that was a result of the t star over t on the outside. And of course, everything equals this. So what we're saying is we can find a forward rate, any forward rate for any period of time, using this relationship between spot rates right here. So if we can find the spot rates for for t star plus t and for t star, if we put it into this arrangement, we can find the spot rate for any point in time. Rather than we're drawing a timeline and figuring out what we need, we could just use this. Let's see if that works. Okay, so this is what we left off with. This is the forward rate model, just expressed in a different way. We just use algebra to isolate the forward rate on one side, to express it all as a function of spot rates. So let's say that this is the situation we have. We're looking for F14, a rate that begins at period 1 and lasts for 4 periods. So we know that at the top of the line, we're going to need to fill in the gap from 0 to the beginning of the forward rate time period. And of course, we need a forward rate for the whole span of time, which is 3% here. That's an R5. So we need two R's here. If you look at the formula, we need R, t star plus t, which t star plus t is R5, and we need R t star, which is 1. And if we just plug in the numbers, we should be able to solve for whatever F14 is. So let's find out if that works. We need 1 plus the rate here, 1.03, over 1.02. And that is to the power of t star over t. T star is 1, t is 4. And then we multiply that again by the numerator on the outside, 1.03. And that should give us F14. And that'll give us 1.002442 times 1.03, which equals 1.032515. And we have to subtract 1 off of that. Therefore, F14 is going to be 3.25%. And you can always check if this is a 3.25% by doing it the other way. You can take a 1.03 to the 5 must equal 1.02 times x to the power of 4, and solve for x. Remember, x now is 1 plus the term, so you have to get rid of the 1. This thing here as well, what we just solved, equals 1 plus the term. That's why we got rid of 1 at the end, because we just want to isolate F14, 3.25. So again, let me point out something we've done here, no matter how we come to the forward curve. Here again we have an upward sloping spot curve. Short rate is 2, the long rate is 3. So R5 is greater than R1, we have an upward sloping spot curve. Therefore the forward rate, this forward rate here, will be higher than this 3%. It should be. The forward rate should be higher than the 3%, and it is. We get 3.25%. So our forward rate beginning in year 1 will be greater than the spot rate for the 5-year period, for the full year period. And forward rates will rise as T-star rises, which means if we had a spot rate for a 2-year period and the 5-year period, we can calculate an F2.3, and we will find that that is higher than F14. So as we keep going higher, as long as the spot curve is upward sloping, each successive forward rate will be higher than the previous. If it were downward sloping, if R5, our 3% here, were less than R1, so let's flip it around, let's say this were 2% and this were 3%, we have a downward sloping curve, then the forward rate we would have gotten would have been below R5, would have been below the 2% if it were reversed. If R5 equals R1, what we're saying is that we have a flat spot curve, a flat yield curve. The forward curve will be flat, and the forward curve will equal the spot curve. All the forward rates will equal the same spot rate as R1, R2, R3 onwards. So just to sum up what I said on the last screen, if we have an upward sloping spot curve, so let's say that R3 is greater than R2 is greater than R1, that implies that the forward rate for 1.1 will be greater than R2, and forward rate for 1.2, which is, this is a, when did these both start in 1 year? This just happens to be a 1-year rate. This is a 2-year rate. So F11 will be greater than R3, and F12 will be greater than F11. The 2-year forward will be greater than the 1-year forward, even at the same time. So this is an example of actual data, and I just did a screen capture from the text to show you this. The spot curve is the dark line. This is from July 31st, 2013, and each curve above it is one successive year outwards, July 14, 15, 16, 17. So what is this saying? When we look at this, what can we take away from this? What are we expecting? We're expecting, let's go all the way to the top curve, July 2017. We're expecting that when we're in July 2017, this will be the spot curve. So that if this is the spot curve today in July 2013, that over the next 4 years we expect interest rates to start moving to end up looking like this. We expect the spot curve to evolve to what the forward curve looks like. Now, how does that make sense? How do we even arrive at that kind of conclusion? Well, keep in mind, every forward curve is derived from the shape of the spot curve. The shape of the spot curve is sending a message to the market about what future expectations for interest rates will be when that time arrives. So built into today's spot curve is the market pricing in next year's or next month's spot curve, so that we expect that the spot curve will evolve over time through these other forward rates. So by the time we get to July 2014, our spot rate should look like this. Now, if our spot rate looks like this, our next forward rates will continue to look like this because nothing has changed. But if the spot rate doesn't evolve this way, let's say that the spot rate comes up a little bit but tends to just do this, then all these forward curves change, because the spot rate is telling us something about what the market expects the future to look like, and the forward rate is derived from the spot rate. So as the spot rate changes, all the forward rates will change as well. So there's something in here now, we're going to get to it a little later on, about our expectation about the future spot rate versus what the existing forward rate looks like today. Keep that in mind. Note, forward rates will not extend further than the furthest maturity on the spot curve. Notice they all end at the same time. You can't go any further because there's no spot rate to imply a forward rate past that point in time. So our spot rate, R30, is the longest spot rate. So let's say we wanted a rate that started in 4 years. The longest you could get is a 26-year term, because inside the brackets, these two terms, T star plus T, that's T star plus T, right? So these two terms must add up to 30. If we were looking for F13, what's the longest term that we can get in here? 17. Has to add up to 30. You can't go past the 30 mark on that. Okay, and just so that we don't sort of get the impression that all yield curves are upward sloping, let's look at a downward sloping yield curve. The dark line is the spot curve. Every other line is a forward curve, and the further out in time we go, this is December 2010. The spot curve is of December 2006. So we can see the further out we go, the lower the spot curve goes. So if you were paying attention, you probably came up with a little bit of a curiosity. If this is an upward sloping spot curve, and this is a downward sloping spot curve, and we're saying that the forward curve, if we have an upward sloping spot, and if the forward curve lies above it, and successive forward curves lie above that, and that if this is the evolution of the spot rate, that in a year it should look like that forward curve, which in a year should look like, aren't we talking about ever and ever increasing rates? Isn't the forward curve, if we draw out enough of them, aren't they implying that rates will just continue to fly to the sky? And same with this one. If we have a downward sloping curve and the forward curve is plotted below it, and each successive, as we go out further and further in time, is plotted below that, aren't we saying that if rates are down, if we have a downward sloping yield curve, isn't the market saying that rates are just going to continue to fall and fall and fall forever? Well, no. Mathematically, the forward curves are derived from the shape of the spot curve. The shape of the spot curve is dictated by sentiment and expectations and feelings today. So that if we look out 1 year at what the forward curve is 1 year out, we would say, given our feeling today and the shape of the curve today, that's our best guess of where we think the spot curve will be 1 year from now, from where we stand today. Somebody else may say, I think that's wrong. From where we stand today, the market is pricing in that particular forward curve, but I believe that to be wrong. And maybe a lot of people in the market believe that to be wrong. Then they will start taking actions, and those actions will change the shape of the spot curve. And if you change the shape of the spot curve, you mathematically change the shape of the forward curve until it reflects what everyone believes the opinion to be. So it's not a matter of, well, if that's the forward curve, that's what interest rates will be in a year. No, that's the expectation based on the current shape of the yield curve. And the shape has information. That's the key thing you're getting out of this chapter is the shape of the curve has a message and has information about what the market believes the future is going to look like from where we stand today. All right, well, we're almost done learning objective A and B. I said I would take the time on this one. I want you to be very clear all the steps we made to get to those last few statements I made on the last 2 or 3 screens. Let's look at the relationship between the yield to maturity and spot rates, and we're going to see if our yield to maturity is our actual return if we held the bond to maturity. Would we actually get the yield to maturity? And this is a common misunderstanding among students when they first get the bonds, that if you calculate the yield to maturity, the thinking is, well, if I hold the bond to maturity, that's what I will get. Not always. So let's see what we have here. The yield to maturity versus the spot rates. The yield to maturity can be seen as a weighted average of the spot rates used in the valuation of the bond. The proper way to price a bond is to discount each cash flow by its respective spot rate. So if we have a 2-year bond, we would discount each of the coupon payments by its respective spot rate at that time, as opposed to using just one discount rate. So to calculate the yield to maturity, we have to do 2 things. Number 1, we have to take a bond, find its present value. by discounting each of the cash flows by its respective spot rate. Once we have the present value, we can then calculate a yield to maturity. So let's have a look at a situation or an example, because I think it always works best if you run right to the example and get it done, right? Let's say we observe spot rates R1, R2, R3, 9, 10, 11. And our yield to maturity, we're going to let it be Y and in brackets T. So we're going to try to find our yield to maturity here. Okay, let's start with a 6%. So we have a coupon paying bond now. We've done zeros up to now. Now we're going to bring in some real bonds here, right? 6% 2-year annual, face value of 1,000. So it's got a future value of 1,000. It's a 2-year bond, pays annual payments of 60. What is the present value of this bond given these spot rates? Well, what we have to do is to find the present value. Let's find an offsetting color here. Present value will equal, our first payment is 60. And when do we get that? In 1 year. We'll discount that by the 1-year spot rate, 1.09. Then in 2 years, we'll get the face value plus our 60, and we'll discount that by the 2-year spot rate of 1.1 squared, and we will get 931.08. So the present value of this bond is 931.08. Now we're in a position to solve for yield to maturity, 931.08. And you can do this two ways. Equals 60 divided by 1 plus YT, that's what we need to figure out, right? Plus 1,060 divided by 1 plus YT squared, and then you just solve for YT. Whatever value of YT equates this, that's your yield to maturity. There is an easier way to do this, right? We know our present value is what? Negative 931.08. We know our future value is 100. We know that our N is equal to 2, and we know that our PMT is equal to 6. All we have to do is compute IY, and you will get your answer. We will find that Y2, because this is a 2-year, our Y2, is 9.96947%. 9.96947%. Let's take a 5% 3-year annual, and let's do the same thing here, and let's see what we get. This is a 6% 2-year. We're going to go with a 5% 3-year here. First of all, we have to find our present value, and it is equal to, well, we're going to get 5, we're going to get 5, and we're going to get 105. There's my numerators all done. All I have to do is do my denominators now. So 1, 2, 3 years. The first one will be discounted at the first rate, 1.09. Then we'll discount the second cash flow at the 2-year spot rate, 1.1 squared. And finally, 1.11 to the power of 3. I get 85.49. So with that in mind, I know that my present value is equal to negative 85.49. My PV will equal 100. My N is equal to 3. And my PMT is equal to 5. All I have to do is compute IY, which is my Y3, which will be 10.93%. 10.93%. Now, let's see what we've done here. What do we have in this case? We have our Y3. You'll notice 10.93% is less than R3. The yield to maturity is less than R3. In this case over here, what do we have? We have our Y2. Our Y2 is less than R2. So our Y2 is greater than R1 but less than R2. Why is that? Because the yield to maturity is a weighted average of the spot rates used in the valuation of the bond. We're gonna look at what happened. We're gonna answer our question about whether or not we get the yield to maturity shortly. I just want to position in your minds exactly how yield to maturity sits in relation to the spot rates. It is a weighted average of those rates, weighted by the size of the cash flow. So if we look at this particular one, the 2-year one that we did, the big cash flow is in year 2. It's discounted at 10%. The small cash flow, 60, is discounted at 9. If it's a weighted average, we would expect the yield to maturity to be pulled towards the 10% because it's got the greater weight. And we see 9.969 versus 10. Whereas this one here, we have 3 cash flows. We would expect that the weighted average to be pulled towards the largest cash flow, and it is 10.93 versus 11. So the longer the term of the bond, the less the final amount will pull our yield to maturity towards it, the less that it will pull. All right, so now that we know how we arrive at that measure yield to maturity, we can ask ourselves, if now remember now, every cash flow is discounted by its corresponding spot rate. So if the yield to maturity is the weighted average of all the spot rates, is the yield to maturity the actual return you will realize at maturity? Now you may be still thinking, but hang on a second, if I buy it at one price and I get all the cash flows and I get my principal, yes it is. Careful now. The yield to maturity, is it the expected return on a bond? Well, it is if it is held to maturity. Number 2, all coupons and principal payments are made in full. And the big one, which is difficult to support, is coupons are reinvested at the yield to maturity rates. Well, how did we get the yield to maturity? Remember now, we have an upward sloping spot curve. How did we get that yield to maturity? It was the weighted average of these spot rates. Is it going to work out such that as time goes by, this curve will move its shape and location to exactly where the weighted average was? Probably not. Typically does not hold. Coupons are not reinvested at the yield to maturity rate. So that typically does not hold. So the yield to maturity must have all 3 of these conditions. This is the one that's difficult. Held to maturity, yeah, go ahead. All coupons, principal payments made in full? Well, sure. It's the minority, the small minority of bonds that the default, not the majority. So that's not a big stretch. Number 3 is what ruins it, and we're gonna show some examples here. Yield to maturity is a poor proxy for the expected return on a bond if interest rates are volatile, because this will change shape, and if this changes shape, guess what? The weighted average rate of return, the weighted average yield changes, and wherever you thought your reinvestment rate was going to be will change as well. The yield curve is steeply sloped either up or down, because that doesn't get maintained for long. And points 1 and 2 affect your reinvestment. So your reinvestment will not be made at the yield to maturity under these conditions. Significant risk of default, well, your cash flows will differ, and embedded options, your holding period may differ. But if there's no significant risk of default and there are no embedded options in the bond, you still have this situation here. All right, so let's just go a little bit further into this one and look at our realized return or our actual return. A realized return is an actual return, and you can't measure your actual return until you actually get your return. But what we can do is we can look at an expected return, and we can see if an expected return will equal a yield to maturity. Once we show that the expected return doesn't necessarily equal the yield to maturity, and probably doesn't equal the yield to maturity, we can then ask, well, if we expect certain things to happen, then our realized return should be our expected return and not our yield to maturity. So let's have a look. Let's take a 5-year annual at 10%. Here we go. 5-year annual at 10%, so we'll have 10, 10, 10, 10, and 110. My numerator is just the definition of the bond, 10, 10, 10, 10, and 110. My denominator is a reflection of the current yield curve. I'll discount my first year payment at the 1-year spot rate, 1.05. Notice it's 56789, 56789. So I'm discounting each cash flow by its respective spot rates. I get a present value of 10543. So my yield to maturity, I know my present value, I know my future value, my N and my payment. I can compute my yield to maturity, 8.6178. Now, I'm saying to you that is not your expected return. The 8.6178 is just a weighted average of the current spot rates used to discount those cash flows. That's all that is just a weighted average. It's not your expected return. Your expected return is built into the forward curve, because the current spot curve is telling us something about the expectations for the future, so that if we had to reinvest this 10, because we're going to get 10 in 1 year, we would be reinvesting it at what we think the forward rates would be, because in a year, these forward rates should be the current spot rate. So let's just have a look and see what we would get. Notice if we use our yield to maturity, we're saying we need to reinvest our coupons at 8.6178%. But the forward curve is saying, hey, look, given this spot curve, the 1-year forward rate is 7%, not 8.6178%. It's only 7%. So your $10 would be, if the expected future spot prices play out as the forward curve suggests. In other words, the market's got it right. The market's priced in its expectation, and the expectation will become reality. Our 10 will be reinvested at 1.07 for a year. Then it will be reinvested at 1.09, then 11.1, then 13.1. The next $10 we get will be invested at 109, 111, 113, then 11, then 13, then 13, then finally we get the 110. You notice that I've just walked myself through each of the rates as I got each of the coupon payments. And so this is what they will add up to. They will add up to a total of 162,226. So now I can calculate my expected return. I'm getting, this is my principal and all my coupon payments back, along with all the compounded interest that I'll be receiving as well. So I will be getting, at the end of the 5-year holding period, I will have received 162.2264, and I will have only put out 105.43. That's the present value that I arrived at. If I divide that by 105.43, I will get 5353.871%. But that is called a holding period return, you'll recall. So if I take the proper root, add 1 to get to 153, or 1.53, sorry, 1.53871, and take the fifth root and subtract 1, I'll get 9.0012%. So, given this spot curve, that's the price of my bond today, 105.43. Given that that's the price of my bond today and these are the cash flows, this is my yield to maturity, which is a weighted average of this spot curve. But this spot curve tells me the forward curve looks like this. And if the market's got it right and the forward curve eventually becomes the spot curve, my reinvestment of coupons will happen at these rates, which means that my expected return on this bond today, given these spot rates, is 9%, not 8.6178%. So our expected return is not our yield to maturity. Our yield to maturity really is not what we're going to earn. It's what we could earn if all of those conditions I mentioned earlier work out. Reinvestment is the one condition that just doesn't have any real reason to work out. So I think we've satisfied all the conditions of A. Let's just read A again and make sure we got it, the learning objective to A. Just because we had a long road, let's just put it in perspective. We should describe relationships among spot rates, forward rates. We've done that. Yield to maturity. We've done that. We've seen that the relationship from the yield to maturity is really a weighted average of the spot rates and not necessarily an expected return. Expected and realized returns on bonds. So we have looked at expected returns. Realized is just exactly what you're going to get. And the shape of the yield curve. So A. B. Describe the forward pricing and forward rate models and calculate forward and spot prices and rates using these models. We have done that. A and B are done. Why did I take so long on this is because as we move down through each of the next few learning objectives, if you don't have this solid, if you don't really see all these relationships, everything's going to become very difficult to understand. So if you don't get this or you're not quite there, read the text. Actually, it's a terrible read, but it'll make more sense now that we've gone through it. A lot of it will make more sense. Or rewatch up to this point again. I think you're going to invest, an hour to redo it again. But this 1 hour that you reinvest again from the beginning to now is going to pay dividends, right? All right, we're starting our next learning objective now, which is to describe how zero coupon rates, or spot rates, may be obtained from the par curve by bootstrapping. This is not a really important learning objective. I'll tell you that straight up. If it was an important learning objective, it wouldn't be presented in the way that it's presented in the text. It would have been played out a lot better than that. So it tells me that that really it's not that important. We really just want to get the concept across that there's another curve called the par curve. What that par curve is, that you can use it to get zero rates, but that's kind of like saying, look, if you have orange juice, you can use that to determine that it came from oranges, and you'll see what I mean shortly. It's kind of looking at it after the fact. And we'll look at something called bootstrapping, but here again, it's the wrong context to look at bootstrapping. We should be looking at bootstrapping in how we arrive at a par curve, not how we use a par curve to arrive at spot rates, and I'll show you what I mean here in a second. The par curve, what does it represent? It represents yields to maturity on coupon-paying government bonds priced at par. So what we would do is we would take government bonds and for whatever coupon rate they have, whatever they're selling at, and we would say, well, what would they have? What would the coupon be if we did price them at par? And that would draw out a par curve. In other words, what payment would be required given a series of spot rates to make the present value equal zero? Notice what I said here, given a series of spot rates. So we arrive at a par curve through a series of spot rates. For instance, let's say we're looking at a 2-year semi-annual government bond, and we can observe the spot rate for the 6-month spot rate, the 1-year spot rate, 1.5-year, and 2-year spot rates. We can observe those. Well, then we can ask the question that, well, let's take our coupon, and obviously since it's semi-annual, our coupon over 2, plus our next coupon, plus the next one, plus the principal amount, plus coupon over 2, equate that to 100. And if these are the observed spot rates, what would this bond's coupon have to be to make it par? That's all it's doing, is it's just taking observed spot rates to get to that par rate. It's important to understand that to get to this par yield, you must have all of the spot rates. And this learning objective is asking us to, given par yields, see if we can figure out the spot rates. You would never have to do that in the real world because you cannot get the par yields unless you have the spot rates. You cannot make orange juice unless you have oranges. So if I hand you a pitcher of orange juice and I say, show me how this was derived from oranges, no. The proper question is, given oranges, show me how to make orange juice. Once I make the orange juice, it is obvious that I must have had the oranges to begin with. Given a par yield, it is obvious that I must have had the spot rates to begin with. But let's just say that you're suddenly handed a par yield curve that's derived from someone and it's on your screen and you look at it and you say, there's the par yield curve. I don't have the spot rates that went with this. Can I work my way backwards? Well, okay, we'll say that, right? Anyways, in this equation, if you solve for C, that's the par yield. It is the coupon that will equal the yield to maturity, coupon will equal yield to maturity when the present value is 0. And again, we're using observed spot rates. Typically, you would use on-the-run bonds to create the par curve, since they are typically priced at or close to par on the day they're issued. Typically on-the-run or recently issued bonds are priced very close to par, so we can look at their coupon, and that could stand in for the par yield. Okay, well, let's demonstrate this bootstrapping method given, and I make the word up here very clear, given these par yields. So we're not going to derive the par yields, and the curriculum makes it very clear that that's really not what's required of you. You're not required to derive the par yields. We'll start from that, but I do want to be very clear. If I showed you how to derive the par yields, you could not do it without the spot rates, which means you would have had to know them first, so that using a par curve to find the spot rates doesn't make a lot of sense because they would have existed before you could calculate the par yields. So this is sort of like Jeopardy, where here's the answer and now you have to frame it in the form of a question. Here's the par yield. What is the spot rate, Alex? So But anyways, I guess the purpose here was to show you the bootstrapping method. But again, I gotta say this, I have to because it bothers me, is that we could have easily shown you the bootstrapping method by showing you how to get the par rates. We could have easily have shown you how to do that. But now we're gonna give you the solution and work backwards and show you how to derive what was needed to come up with this anyways. All right. It frustrates me when I see things done sloppy. Anyways, let's look at the 1 year spot rate. And again, we're going to use a unit of 1 to do this. So 1 equals, what do we have? We have 5 on this one. That's all we're going to get is 5% on the 1 year. That's the par. So it matures in 1 year. We'll get 1.05. And of course, we have to discount it by whatever the required return is, whatever that spot rate is for that period of time. Since we don't know it, we'll just put R1. Doesn't take much to see in this case that R1 is going to be 5%. Let's go on to the 2 year spot in this case. What do we have here? We have 1 has to equal, and our coupon is 5.97%. So we'll have 0.0597 plus 1.0597. There's our numerators. This first payment will discount at R1. R1 is 5%, so we'll discount this at 1.05. And this one will discount at R2. And of course, since it's at the end of the second period, it's squared, and we simply solve for R2. So I'll go through this one, and then after that you'll pretty much have it set up for yourself. I'll just do these ones quickly after. So this will be 1 equals 0.056857 plus 1.0597 over 1 plus R2 squared. 1 plus R2 squared will equal 1.123587, and we can see that R2 will just be the root of this minus 1 is 5.99241. If I didn't round off all the time, you would have found that you would have gotten 6%. So we have R1 and we have R2. Let's calculate R3, and R3 will just be our missing number here, and it'll look like this. Our yield, our par yield is 691. That is the coupon rate that makes this particular bond equal to par. That's why it's called a par yield, right? So what do you have? We have 0.0691 for 1 year plus 0.0691 for 2 years plus 1.0691 for our payment. There's our 3 numerators. We just need to discount this by our denominator. By the way, of course, that's 1 equals. By our denominator, what's our 1 year spot rate? 1.05. What's our 2 year spot rate? 6. 1.06 squared. And then this will be discounted by 1 plus R3 to the 3. We solve for that one. You'll find that R3 equals 7%. Sorry, R3 equals 7%. This is why it's called bootstrapping, is because you couldn't figure out R2 until you had R1, because you can only have one missing variable. You couldn't figure out R3 until you had R1 and R2. Now we can figure out R3. And you can't figure out R4 till you have R3. So you have to figure out 1 to get the rate that allows you to figure out the next one, to get the rate that allows you to figure out the next one, etc. So the 4 year spot rate, I think you can see where this is going. What is it? 7.81. So we have 0.0781 plus 0.0781 plus 0.0781 plus 1.0781. That's a point. There's my 4 numerators. You'll notice that I do this a lot. I don't write out each one on the way. I tend to want to do all my numerators first, just so that my thinking is clear. And then, of course, I'm looking at just my denominators. My 1 year spot, R1 is 5. My 2 year was 6, 1.06 squared. My 3 year was 7, 1.07 to the 3. And this will be 1 plus R4, of course, to the 4. And you solve for R4. R4 will equal 8%. So, well, what was the value of this particular reading if we could have shown you how to do bootstrapping to actually get the par curve? Well, the idea is that we're not really trying to show you how to get a par curve. We're just pointing out that a par curve is a very specific thing, and this is going to become important when we move on to swaps and we talk about par bonds. We're not talking about the par curve. And we're showing how the par yields, we can derive the spot rates for them, because honestly, the spot rates were needed to get to the par yields. It's just like the forward and the spots. You can use the spot rates to get your forward rates, and you can use your forward rates to go backwards to your spot rates. Same thing here. So the par yields are related to the spot rates, so you can move towards them, or given the par yields, you can move back towards the spot rate. Okay, so we're on LOSD. And a word here. D says, describe the assumptions concerning the evolution of spot rates in relation to forward rates implicit in active bond portfolio management. And if you've read the curriculum, the section in the chapter that explains this, you probably have thrown your hands up in the air several times going, what? What? It is so poorly written and so unnecessary. It's complicated for no good reason. I don't know why the authors do this, and the only reason I can find why authors write in a very complicated way for no good reason is they themselves don't understand it well enough to realize its simplicity, that they're still working their way through it, so they don't know how else to describe it, or they're just repeating stuff they read somewhere else and they don't really understand what they're doing. So I'm going to show you how absolutely simple this is by showing you 3 scenarios, bringing them together and saying, look, this is really all it is. You don't need all of those, all of the notation that they introduce. That is just a huge pile of crap and a waste of time. You don't need it. Let me show you. Here's our original scenario that we've looked at, right? We have 3 spot rates, a 1-year, a 2-year, and a 3-year spot rate, 9, 10, 11. So we're facing an upward sloping yield curve. We know how to calculate this forward rate. We know how to calculate this forward rate. And if we wanted the 2-year rate, we know how to calculate that. That's great. We can also calculate the discount factor for the 1-year 0, the discount factor for the 2-year 0, and the discount factor for the 3-year 0. And we know that these forward rates are the rates implied by these spot curves. So we should be today indifferent between buying a 3-year 0 versus buying a 2-year 0 and then taking the forward rate at that point in time for 1 more year, or buying a 1-year 0, rolling it over into a 1-year forward at time 1, and then rolling all that into a forward at time 2. All 3 of those routes should produce the same result. We should be indifferent between them. That is, if the future looks like what we think it looks like from today. So that after a year, if the curve was right, and everyone agreed with the curve, and the spot curve evolved and moved into the forward curve. In other words, in a year from now, the spot curve will be what the forward curve looked like a year ago. It will look like what it should be today. So let me do this. Here we are with 2 years here. Here's the 3 years. Let's say a year has gone by. That's out of the way now. What would be the 1-year spot after this year has gone by? We can't say 9% because, well, that's history now. So the 1-year spot is this forward rate. And you'll recall that we had, when we calculated that forward rate, we calculated it as 11.01%. So this over here was 11.01%. This was 13.03%. And this whole thing that we calculated before was 12.02%. This is F12. So the R1 will now be 11.01%. This 2-year spot rate, since we're here now, the 2-year spot rate will be the F12. This will be 12.02%. And this over here, this F1, this F11, that's what this is, will now be what F21 was, which is 13.03%. So this is what we mean when we talk about the evolution of the spot curve into the forward curve. As this time has gone by, this forward rate that we had calculated here now becomes the current spot rate. This forward rate now moves down one and becomes the next period forward rate, and the 2-year forward rate from today now becomes the 2-year spot. That is if all of the thinking that went into all of these spot rates and all of the trading ended up being exactly what everyone thought it would be in terms of the forward rates. So that in a year, the 1-year spot is no longer 9%, the 1-year spot is now 11.01%. So if we calculate discount factors for these, we can now, because we have the 1-year spot. We'll get a discount of 0.900819, and we'll get a discount factor here of 0.7969. Again, I'm stressing that the spot curve evolved, changed its shape and size to match what the forward curve was after 1 year has passed. Great, beautiful, we get that, right? All right. That's going to become important now, because I'm going to change this assumption. I'm going to say, well, hang on a second. The spot rate doesn't necessarily have to end up being what the forward rate is. Maybe things don't change at all. Maybe a year from now, the spot rate is still 9%. So that we're thinking that it's 11.01 and now it's only actually 9. Wouldn't that mess up a whole bunch of things? Of course it will. Let's see how. Anyways, so right now we're just assuming that everything worked out. Everything worked out perfectly. The expectation has become the reality. After 1 year, let's figure out what our returns are if on day 0 we bought the 1 year, the 2 year, and the 3 year. At the end of the first year, what is our return so far? Well, at the end of the first year, the 0 is gone. The first 0 is gone, right? So we can figure out our actual return. We have an actual return at this point. And of course, remember now, we got 1 and we paid 0.9174 over 0.9174. No coupons, no nothing, so it's just a change in price. That's easy to see that we made 9%. 9%. There we go. 1 year has passed. That was a 1 year 0. That's all we could make. Let's go to the 2-year spot and see what we made. And we can do this 2 ways. Let's do it one way is to say, well, the 2-year spot, when we entered into the 2-year 0, when we entered into the 2-year 0, 1 year has passed. It's now only a 1-year bond. It's now only a 1 year 0. And if this is the spot rate for a 1 year 0, we can tell right now that, well, it's 1 discounted back by 1.1101 will equal 0.900819. That's what it should be. Well, another way of looking at it is it was 82664, 0.82664. So over the course of the year, if that was the discount rate, it must have made 1.09. And if we multiply that, we will get 0.900819. What is our return? It shouldn't take much to see, right? We'll get its market value now is 0.900819. It was originally 0.82644. If you divide it by 0.82644, we will get, lo and behold, 9%. Well, we have one more to go through. What is the 3-year spot? What's the value of the 3-year spot after 1 year? Well, after 1 year, what do we have? It's nothing more than a 2-year spot, and the 2-year spot rate is 12.02. So we can take 12.02 squared, or we can take each of the rates. So we can discount it by 1.1101 and multiply that by 1.1303. If we discount that back, we will get 0.7969. You can try discounting it back by 1.1202 squared. You'll get 0.7969. And you can start with 0.73119 and multiply it by 1.09. You'll get to 0.7969. No matter which way you'll do it, you'll get to it because we started from this assumption. All of our rates and our discount factor started from this. We ended with exactly what we thought it would be, so the math has to stay the same. Well, what's our return here? We end with a value of 0.7969. We started with 0.73119 on the 3-year. Divided, of course, by 0.73119. What do you think it's going to be? 9%. So on an upward sloping yield curve, if we bought the 1-year zero, over the course of the year, we make exactly what it was, 9%. If we bought the 2-year zero and the spot curve evolved exactly as the forward curve implied that it would, we'd make 9%, the same spot rate for the year 1, same with the 3-year. That's what we would make. And this would be our new spot curve, 11.01 and 12.02 for the 1 and 2. And our forward rate 1 year out would now be 13.03. All right, let's change the assumption. And this gets a little bit interesting and probably a little illuminating, that you might not have known this relationship. After I'm done, you might go, oh, I didn't know that. That makes sense now. But hopefully it will. I know that for when I do it in class, I do get some, oh, okay, now okay. But let's say now that instead of this is our original scenario here, and you'll recall, again, this rate here was 11.01. This was 13.03. And, of course, our 2-year in here was 12.02. So given on this date, this observation of spot rates, this is what it was implying for what the forward rates would be. If the market didn't think that those were the rates in the future, the spot rate today would not look like this. It just wouldn't. It would look like something else to reflect what the belief was for the future. Well, let's say it's wrong. The market was wrong. I mean, that never happens. But let's just say it's wrong. And let's say instead of 11.01, the 1-year spot now is 10%. I want you to see something here. In this scenario, on day 0, the 1-year spot rate is 9%. 1 year later, the 1-year spot rate is 10%. So interest rates have gone up. The spot rate did go up. It just did not get to what the forward rate was by the spot curves that would have implied that it should have been 11.1. In other words, it didn't get to that rate. It didn't get there. The 2-year spot rate is now 11% instead of 12.02. And if we have 10 and 11, we can figure out the implied forward rate for F11. It'll be 12%. So that rate will be 12%. Our discount factor, if this is 10%, is 0.90909. Our discount factor for the 2-year spot is 81162. Let's see what our return is. For the 1-year spot, it'll always be 9%. Why? Because 1 year has passed. 1 year's passed, so it will be what it will be. What about the 2-year spot? How do we calculate that on the 2-year spot? Well, the 2-year spot is now 1 year. There's only 1 year left, and since the spot rate is 10%, it has a discount factor of 90909. That's its price. So after 1 year, the 2-year spot we bought at 82644 is now priced at 90909. So we can take 0.90909 minus what we paid, 0.82644, divided by 0.82644. We will get 10%. Not 9, we got 10% now. So we made more than the 9%. What about the 3-year spot? What happens there? Well, our discount factor is 0.81162. We paid 73119, so all we have to do is say, well, it is now worth 81162 given what the spot curve looks like. We did pay 0.73119. So I'll divide that by what I did pay, 73119. I will get 11%. Look what happens here. If the spot curve evolves exactly as we expected by the implied forward rates, we make 9. After 1 year passes, we will make the 1 year spot rate no matter what we do. No matter what we do. We're not going to get excess return if everything works out as it's implied. However, if the market is wrong and spot rates do not converge to what the forward curve would look like, the spot curve doesn't change its shape and size and end up there, maybe it changes it but not enough, we can actually make more than the 1-year rate by buying a longer term bond. So in the first scenario, it didn't matter if we bought a 1-year, a 2-year, or a 3-year zero. After 1 year, we made 9% in all cases because the market had it right. If we think the market has it wrong and spot rates will not in 1 year rise to the level of the forward rate, we can do better than a 1-year return of 9% by buying a longer term zero. We can buy the 3-year zero and then sell it after 1 year. We'd make 11% instead of the 9%. Even if our holding horizon, our investment horizon was 1 year. We go in the market, we say, I'm in for 1 year and I'm out. If we look at the forward curve and the spot curve and we say, I don't see that happening. I don't see spot rates rising to the level of the forward curve in that 1 year period anytime soon. We can do better by buying a longer term bond than by buying a shorter term bond because of our expectation that the market has it wrong. In fact, we would say at this point, the market has bonds undervalued. One more scenario. All right, so here's the new scenario. 1 year has gone by. The 1 year spot rate is now 12%. Last year it was 9%. Now it's 12%. When it was 9%, the implied forward rate here was for, if you recall, 11.01. This was 1303, and of course, remember this was 12.02. Well, 11.1%, but now it's 12. It's 12, and instead of 12.02 on the 2-year spot, we have 13%. A combination of 12 and 13 gives us an implied forward rate of 14.01% here. The 1 year spot, we just discount it back by 12%. We'll get 0.89286 as the price or the discount factor. And there's the discount factor on the 2 year spot. What have we made? Remember now, on day zero, way over here, we can buy the 1 year, the 2 year, or the 3 year zero. If we agree with the shape of the curve, if we think in a year from now, yeah, that's what it's going to be, and our investment horizon is 1 year, it makes no sense to buy anything but the 1 year. If we think, no, it's not quite going to get there, it's just not going to get there, we saw that we can go, well, we may as well buy the longer term one because we'll make more in the first year. Now we're saying rates will be higher than the spot rate. Let's see what we made on our 2 year bond. Well, our 2 year bond at this point, we paid 82644 to get it. And after 1 year has passed, it's now only a 1 year zero. So we'll discount it back by the 1 year spot rate. It's 89286. So we have 0.89286 minus 0.82644 over 0.82644 gives us 8.037%. We didn't even do 9%. We did worse now. And we can do the same with the 3 year bond. After 1 year, it's a 2 year bond, so we'll use the 2 year spot. And to get a discount factor, 0.78315. What did we originally pay? 0.73119 over 0.73119. That gives us 7.106%. Well, we would have done better by just buying the 1 year spot. The 1 year spot. Let's bring it all together now. Okay, so I made a nice little chart here that has everything in here. I'll explain the columns and then we'll do some narration here. This column means after 1 year, we're going to look at what happened to the 1 year zero, the 2 year zero, and the 3 year zero after 1 year has passed. This column means the spot evolves to the forward curve. Here the spot rises, but not to the forward curve. And here the spot rises above the forward curve. And of course, this is what we expect to happen in the future. The expected future spot prices here end up converging to what the forward prices were on day zero. Here they fall below. Here they fall above. Look what happens. For the 1 year, you're going to get 9% no matter what because it's matured. So It's history. It's in the history books. You get 9%. When the spot in 1 year finishes below what the forward curve implied it would be, you would do better by buying long. You'd get a better return in the first year. Even if your investment horizon was 1 year, you could still buy the 3-year, sell it after 1 year, and realize 11%. If the spot rate rises above what was implied by the forward curve on day 0, you would have done better by buying short instead of buying long. So it comes down to this. When you look at a spot curve and the forward curve, you have to look at that forward curve and say, do I think that by the time we get to that point, when time passes to that point, that the spot rate will be in 1 year or 6 months what the forward rate is implying now? Will it be higher or lower? If you think it's going to be exactly what it's going to be, then you will maturity match. That means that if your investment horizon is 3 years, you may as well just buy 3-year bonds. But if you think it's going to be lower, you'll buy long. If you think it's going to be higher, you'll buy short, or you'll short long. You can do the opposite as well. So let's put a little bit more narration on that now that we sort of have that idea. Okay, so let's start with our forward pricing model. You'll recall that it looked like this. If we have a scenario that looks like this, we have a 1-year 0, a 3-year 0. From this, that's enough to find the implied forward rate starting in year 1 for 2 years. Just 1.09 of the power of 3 equals 1.07 times our x squared. Solve for x, subtract 1, and you'll get 10.01. So that our discount factor for this, if we were going to today enter into this forward contract, if we were going to enter in, we'd be locking in a price of 0.8262. And that is basically, so what we're really doing here is we're saying it puts us at an indifference point. So if we could buy a 1-year 0 today, let's say we could enter into a 1-year 0 at 7%, and at the same time we enter into a forward agreement for a 0 where we're going to pay 8.262, it would be the same thing as entering into a 3-year at 9%. That's the whole idea behind pricing the forward. It's implied by the shape of the curve. Okay. So therefore, our forward price will be 0.8262. Now, here are the big points here. As of today, if you expect the 2-year spot rate in 1 year, this is the 2-year, this is the forward rate for a 2-year. So as of today, if you expect the 2-year spot rate in 1 year to be less than 10.01%, you would buy the forward. So let's say that we expect it to be 8% instead. To prove that we would buy the forward, let's say that we expect in a year, the 2-year spot will be 8%, not 10.1%. Well, here's the price of the forward at that time, which would be the price of the 0 in the market, 0.8573. And you're buying it for 8.262. You've already entered into an agreement to buy it for 8.262. It has a value of 8.573 right away. So you would buy the forward. If you think that the 2-year spot rate in 1 year will be greater than 10.1%, you will sell the forward. And let's just use 12% as an example. Let's price out a 2-year 0 at 12%. It'll be 0.7972. But you are going to pay 8.262 for it. If you hadn't entered into that agreement, that forward agreement, you could have just bought it in the market for 7.972. So if you sold it at 8.262, it now has a market value of 0.7972. We can go ahead and short zeros all day long. Why? Because there's no coupon to pay. There's nothing to pay. There's only price change. So this really brings together everything we've talked about. The forward curve is an expectation of what the future spot rate will look like when we get there, based on the shape and the level of the curve today, and of course other things going on in the market. Those other things will change the current price of zeros, which will change the shape of the spot curve, which implies the forward curve. If the market gets it wrong, And if the future doesn't look like what we thought the forward curve was today, I don't like all of these abstract terms, but you get what I'm saying, then there's a trading opportunity. So when we look at the forward curve, we have to say, is the spot price going to be above or below the forward price in 1 year? So saying are interest rates going up or down is not the right thing to do as a bond trader, because interest rates can go up, but not as much as what the forward rate implies, and you can still make a bet on the spot rate not converging to the forward rate. Even if rates go up, they just don't have to go up by enough. So the proper question is not, are interest rates going up or down? The proper question is, are spot rates at some future point in time going to be greater or less than what the forward rate implies today? Okay, so now we're ready to look at this strategy called riding the yield curve. This is LOSE, which asks us to describe it. We can do it in one screen. It's rather simple. It's also called rolling down the yield curve as time passes. And you have to understand from which direction we're looking at. When we think about time passing, I get many students that try to figure out what's going on by moving from the origin outwards towards T as time passes towards T. And I have to explain, no. Time passes this way. You're rolling down the yield curve. Why? Because this is what the yield curve looks like today. Well, in a year, a 10-year bond will now just be a 9-year bond. A 9-year bond in a year will be an 8-year, will be a 7-year, will be a 6-year, blah, blah. So time actually works this way. So if you were having trouble sort of in your mind seeing what that means, just understand that time, we're not moving towards time. Time is in a bond is moving towards zero, because a 10-year bond in a year from now is only a 9-year bond. It's an 8-year bond. It ages towards zero, right? So that's why it's called rolling down the yield curve. Now, why is this important? Well, the bond will be valued at successively lower and lower yields. So if we have an upward sloping spot, that means the forward lies above the spot curve. And here's the big assumption behind this strategy. This is the big assumption. You need an upward sloping yield curve, which means your forward curve lies above it. And if you come to this conclusion, if you say, look, the level and shape of the spot is not expected to change, that means it is not going to evolve to the forward curve. When we say it's not expected to change, it means it's going to look just like that. The forward curve may be over here. So if you think that over the course of the year, the spot curve will not end up looking like this in a year, but will stay this way, then buying bonds with a maturity longer than the investment horizon would provide a total return greater than the return on a maturity matching strategy. Maturity matching means you're matching it with your investment horizon. So if your investment horizon was 1 year, or even 2 years, let's say, and you didn't expect this to change, in other words, it's not going to move up and converge with the forward. It's going to stay right where it is. The level and the shape are going to stay exactly the same in 1 year. So if the 1 year spot today is 9%, in a year, the 1 year spot will be 9%. I don't expect it to change at all. Then you would buy long, and as each year goes by, the bond will be valued at successively lower and lower yields. Well, think about bond pricing. When yields go down, what goes up? The price. There you go. Now, the wider the spread between the spot and the forward, the longer the term of the bond, the greater the total return. So we have spent some time on the spot curve. Now we're going to move to a swap rate curve. And I'm not going to spend a lot of time in deriving a swap rate and explaining what all that is. You're going to see that if in the derivatives reading when you get there, or if you've already been there, then you know exactly what is going on. So if you find that I give that short time, it's because it's really not what we're doing here. We're really looking at the swap rate curve. So we're going to take the swap rates as mostly given to us and talk about the significance of, well, if we put it into a curve, what's the significance of that, okay? But I'll give you just a brief walk into the spot rate so that we understand the spot rate curve. A swap rate is a price quoted in fixed yield, that a fixed rate pair will pay for LIBOR flat. When we say LIBOR flat, that doesn't mean plus or minus any basis points. It's just whatever 3-month LIBOR is. The price is set so that the value of the swap at inception equals 0, and to do that, you simply equate the present value of the two payment streams. And if their present values are equal, you can conceive of a swap as being long one, short another. So if you're long something that costs $100 and you're short something that costs $100, you have a net zero entry. And that's all we're doing here. So the present value of the cash flows from the fixed bond are set equal to the present values of the cash flows from the floating rate bond. And we find our spot rate by taking the ratio of the present value of the floating rate payments divided by the sum of, and we just, for every coupon date, we run a calculation, which is the notional amount times the spot rate times the number of days over 360 between payments times a discount factor. And since we're trying to solve for spot rate, we bring that to the outside and we just solve for this. Again, not going to go into detail, not even going to give you an example of how this is done because you're going to see it somewhere else. There's no sense in doing it twice, right? The discount factor, DF, the discount factor for both streams. We discount to arrive at present value. We discount both streams of payments based on one period LIBOR plus a series of forward rates derived from Eurodollar futures contracts. So that's how we get our denominator in order to discount all of the future cash flows, because you can rightly argue that, well, hang on, if this is a floating rate bond, we know the first payment, but we don't know all the others. Well, we use the forward rates to discount those payments to come up with a present value. Later on, we'll see a shortcut in this where we don't really have to discount anything. We can calibrate the swap rate curve. By calibrate, it means what instrument are we going to base our discount factor off. You can use T-bills, LIBOR, commercial paper rates, bankers' acceptance, certificates of deposit. So you have flexibility in this. The most obvious one and the most common one is LIBOR and is 3-month LIBOR. Well, once we've calculated all of our swap rates, we can plot out a swap curve. In one of the earlier learning objectives we looked at the government par curve. And we didn't really spend a lot of time there. We just sort of introduced the terminology and really what it was. You would recognize a swap curve as a type of par curve. A type of par curve, not a government par curve. It's just a type of par curve. So, what do we got? We got a swap rate curve, but we have a government spot curve. These are both pricing benchmarks. We can value bonds and price bonds out against either one of these curves. They are both a measure of the time value of money. So why would we use a swap curve if we already have a spot curve? It doesn't take much thinking to see that, well, if the spot curve is constructed from treasuries that are default risk-free, and the swap curve is constructed from a reference rate or calibrated with a reference rate like LIBOR, which is an interbank lending rate that is not default risk-free, wouldn't they lead to different valuations? Yes, they would. But here's the thing. If you construct a government spot curve for every country in the world and you tried to price out a bond with those, guess what? You're going to come up with different prices in each one. So let's say that you're an American company and you're issuing a bond in the U.S. What's the appropriate one to use? Probably the government spot curve. But if you're going to issue a bond in another country, whose government spot curve do you use? What if you were going to issue a bond in the euro, not a domestic or a foreign, but a euro bond? Which discount rate would you use? At that point, it would make more sense to use something more international. And which is what the swap rate curve is. It goes beyond borders. But not only that, look at point A. One may be more liquid, and the more liquid one is a better measure of the time value of money. For the U.S., they're both just as liquid, but that's not necessarily true in all markets. So you want the more liquid one because frequent transactions will lead to more efficient pricing. If one is not that liquid, certain parts of the curve are not that liquid, you'll get inefficient pricing and a poor reflection of the time value of money. B, some countries do not have a liquid government bond market greater than 1 year. So even if you were going to introduce bonds in that particular market, that government spot curve would be a poor measure of the time value of money. C, when the private sector is greater than the public sector, swap rates may be more relevant as a measure of the time value of money. In the U.S., that is the case. The private sector is greater than the public sector, but the public sector still, the treasury market is still so deep enough that both of them are relevant as a time value of money. And D, the nature of operations. Let me see if I can give you an example of this. Let's say that you were valuing asset-backed securities. They typically trade at a nominal yield spread at their weighted average life to the swap curve. But if you were doing something like, let's say, mortgage-backed securities, then they would trade at a discount, they would trade at some spread to the government spot curve. So it depends on the nature of the operations, and it would be outside of the scope of this reading to go through a whole list of all of the different types of businesses that would use one versus the other. This is just something you'll learn through experience, that be prepared that some places will use will calibrate or price out their obligations with either the government spot curve or the swap rate curve. So let's have a look at the swap spread. We are aware that the government spot curve is derived from government treasuries, and that the swap curve is derived from a rate based on interbank lending. So we would expect a swap curve to lie above a spot curve, and it does. That shouldn't surprise you. It does. Well, how far above it does it lie? Let's measure that. That's called a swap spread, and it has meaning. There is some information in that spread. So let's define it first. The swap spread is the spread paid by the fixed rate payer over the same maturity on the run government security. We use the on the run because it's the most liquid, so it'll reflect the more relevant interest rate to compare it with. So for example, let's have a look over here. If we were looking at a 5-year swap, and let's say that it was 2% and the 5-year treasury was 1.7%, the swap spread would be measured at 30 basis points at that maturity. Well, what does that mean? It's easy to calculate the spread. All you do is you say, well, if we're looking at a 10-year swap, find a 10-year treasury. 2-year swap, find a 2-year treasury, and measure the difference, the spread between them. So if I were going to look at it in terms of a picture, let's say that this whole rectangle was 2%. That's my swap rate. My treasury rate would make up a certain amount, and then my spread making up the difference tries to capture credit as a sort of a credit spread. I think that makes sense. You're going from a default risk-free instrument used to calibrate the spot curve to a more riskier rate, which is the rate that banks will lend to each other unsecured. So it should capture some element of credit. So there's a credit spread and liquidity. There's a liquidity risk component as well. To really try to see what's going on here, let's have a look at what the swap rate looks like, and let's just draw out a hypothetical swap rate. You can put it into different segments. The very short segment up to 1 year, these are just LIBOR rates that you can see in the market because there they are, right? The going out past 1 year, up to 2 years, typically, sometimes 3, sometimes even up to 5 years, you can use Eurodollar futures. Well, what are Eurodollar futures? These are for deposits of US dollars in banks outside of the US. So they'll reflect a lending and borrowing rate at the midterm, which is kind of like LIBOR, but further away. And then past that, you'll use swap rates. Now, I want you to think about the spot curve in relation to the swap curve, how this swap curve is derived. What rates go into this? What forces in the marketplace determine these? There'll be supply and demand at this level, there'll be supply and demand at this level, and supply and demand at this level, and you'll get a curve that represents the supply and demand along that curve. Now, think about the spot curve, and think about the supply and demand there. If a government runs a balanced budget and has a good, a deep enough treasury market, the spot rates would probably be a good indication of the risk-free rate. But what if a government was running budget surpluses? If it's running budget surpluses, it's not issuing as much debt. If it's not issuing as much debt, it may be even retiring debt. Do the yields on government treasuries reflect a liquid market with frequent transactions? Probably not, which means the rate on treasuries is distorted. It probably does not reflect the risk-free rate. Well, have a look at where we are today, where you have central banks that are actively engineering the curve. So Germany has negative interest rates on the 10-year. Is that a real reflection of the risk-free rate? Probably not. So when we look at the swap curve, while it will be influenced by the rates on the spot curve to some degree, because if there's no yield in treasuries, money is going to migrate to where it can get yields. It will lower the swap rate, but it's a purer measure of the price of risk simply because it's not an engineered curve like the spot curve is. So that spread gives us some information above the treasury rate as to what markets perceive as the risk in the general economy that the central bank tends to depress in the treasury yields when it engages in things like quantitative easing. You lose that pricing ability. You lose the idea of what's the price of risk, whereas the swap curve is more likely to preserve that cost of risk. So the spread above it is important to watch, because if the spread is decreasing, there's a general sense of calm in the market, of willingness to take on risk. And if there's more of a demand to take on risk, the price of risk has to go down, right? But when that spread increases, well, then maybe there's a risk aversion in the marketplace, so the price of risk has to increase relative to a risk-free asset. So we've already introduced the concept of a spread to try to capture a measure of creditor liquidity risk, the swap spread. Let's look at some other spreads and see if we can do a better job at that. And we can move to a Z-spread, a zero volatility spread, which is a more accurate measure of credit and liquidity risk because it can be tailored to every specific bond. In other words, we can look at different bonds and look at their own Z-spread as opposed to just one swap spread per maturity. We could say a bond from this issuer has this Z-spread. This bond from that issuer maturing on this date has this Z-spread. So here's what it is. It is a constant basis point spread that is added to the implied spot yield curve. That is your denominator, so that the discounted cash flows of a bond equal its current price. So here's what it looks like. And let's just start with Z equal to 0. Let's say that there is no spread. And if we discount all of these payments, let's say it's a corporate bond, and we discount all of these payments in the future value by just the implied spot yield curve, it's not going to equal its present value. Because we're discounting a risky asset and risky cash flows with a riskless rate, it's not going to equal its present value. So the question then becomes, well, what would the constant spread, what can we add some constant to each term to make it equal the present value? And that constant is a measure of that particular security's credit and liquidity risk, and we would expect that over the life of the bond, that its spread would be constant. So that while spot rates change and the price of the bond may change depending on where the required rate of return is in the market, the spread over that required return for credit and liquidity risk would have zero volatility. So Z is a constant amount. So let's take an example. Let's take a 4% 3-year annual that's selling at 99.1104. And we have a spot curve of one period rate of 3%, our 2-period rate is 3.5, our 3-period rate is 3.9. So what's our numerators? Our numerators, since it's 4% annual, will have 4, 4, and 104. What's our denominator? Here it'll be 103 plus Z plus our denominator here is 1035 plus z squared, and here it's 1039, the 3-year rate, plus 1 plus z cubed. Solve for z. And you can see that there is no set of keys on your financial calculator that you can hit to solve this. You're going to need a spreadsheet to solve this, and then you simply just enter in a value for z of, let's say you feel it's 20 basis points, and you see how close you get to 99.1104. And if you're not there yet, you might go to 25 or 30 basis points, or 40. If 40 is too high, then you go to 35. 35 is too low, you go to 37.5. And you'll slowly get to the to a measure, and you really only have to bring it to 1 decimal place on the basis point. So this is 44.5. If you put 44.5 basis points, this constant amount, onto each of these spot rates and discount these cash flows, you will find the price. So how do we interpret that? We interpret that to say that if the spot rate represents the risk-free rate of every cash flow, then this particular security as risk is 44.5 basis points higher than that risk-free rate. That is the compensation for the credit and liquidity risk of that bond. Now you can compare that with other bonds, the Z-spread on other bonds, and you could say, well, does this other bond have a higher or lower spread to pay me for credit and liquidity risk? All right, let's have a look at two more spreads, the TED spread and the LIBOR OIS spread. The TED spread is just an acronym, T for Treasury, ED for Eurodollar futures. So it's a spread between the Treasury and Eurodollar futures for the same maturity. So T-bill to Eurodollar futures. T-bill, remember, this is less than 1 year now, so we're looking at LIBOR rate. So whatever the LIBOR rate is minus the T-bill rate for the same maturity. So 3-month LIBOR minus the 3-month T-bill rate will give you a TED spread. If we see an increase in the TED spread over time, it means that interbank risk is increasing, because LIBOR should reflect the risk in the interbank lending market, whereas the T-bill rate is considered a risk-free market. So the spread must be measuring interbank risk. So this reflects risk in the banking system. Some say it also is a gauge of risk in the overall macroeconomy, because if there's stress in the banking system, that means there's stress everywhere. That means that there are problems in other places. You're not going to have just an issue in the banking system without it spilling over into the general economy, or something happening in the general economy and slowly infecting the banking system. So maybe if trouble starts in the banking system, it's going to spill over to the general economy. I think we can pretty much follow that through. But that doesn't necessarily mean that something that starts in the macroeconomy would affect interbank lending. It may have no effect, in which case the spreads may not increase, so you still have a healthy banking system. The LIBOR OIS swap rate is the LIBOR rate minus the overnight indexed swap rate. Well, what is this? This is a floating interest rate of a swap calculated as this. 1 plus day 1, 1 plus day 2, 1 plus day 3, all the way to day 3. This is the overnight rate. So 1 plus the overnight rate times, so it's just a multiplication series. T is the number of days in the payment period, and we're taking a geometric average. So it's the overnight rate, the geometric average of the overnight rate over the period. So it's LIBOR minus the overnight indexed swap. It is an indicator of risk and liquidity of money market securities. All right, so now I think we're getting into some of the more interesting stuff with yield curves, which is some of the term structure theories. And once we go through some of the theories, it does have some value for how you view the term structure of rates and what you think, what kind of information you think is in there, and how useful you think it is. So let's. The first one we have to deal with is local expectations, but it's hard to understand local expectations unless we start with pure expectations. And this is what's called an unbiased expectations theory. What it's saying here, take a look. I'm going to keep this up for each of the theories we go through, because I'm going to draw your attention to it. We have our spot curve, we have our forward curve. We have an upward sloping spot curve, we have an upward sloping forward curve that lies above the spot curve. The forward curve is fully derived from the spot curve. It is the prices implied by the spot curve for what the future short-term rates will be. Great, we get that. What pure expectation says is that the forward curve at any point in time is an unbiased predictor of what the future spot prices will be. So that whatever the forward price is, F11, that is an unbiased predictor of what the spot rate, the 1 period spot rate will be 1 period from now. So that the slope of the forward curve only reflects expectations of future short-term rates and nothing more. So that when we look at that forward curve, we can say all that's reflected in there is the market's expectation of what future short-term rates will be. Now, the theory behind this, if you think about it, sort of makes a little bit of sense. That if we saw some part of the forward curve where we go, we don't believe, the markets believed that short-term rates are not going to be that. Well, suddenly there's a trading opportunity to short the forward and buy the underlying on the Treasury, because obviously we expect the forward rate to drop. So there is some trading that can be done such that once we get to a point where the market believes that the forward curve is a reflection of what the future spot rates would be, there'd be no more motivation to trade. It would be in equilibrium in that point. So if you think it through, you think, well, yeah, okay, so that kind of makes sense. Well, what are the implications of believing that? That's just, now this is just a theory, it's a simplification, right? What's the implication of believing that the forward curve is an unbiased measure of what the future spot prices will be? Bonds of any maturity are then perfect substitutes. They're perfect substitutes. So let's say that you had an investment, a 5-year investment horizon. You should be indifferent between buying 5 consecutive 1-year bonds, between buying a 5-year bond, between buying a 12 and a 30-year bond, and then just selling after 5 years. They should all have the same return. We've already shown that mathematically, that to get the 5-year spot rate, if you invest for the 5-year spot rate, it should be the same as investing at the 1-year spot rate, the return on that multiplied by the return on the first forward multiplied by the return on the second, etc., etc. We've already seen that we can calculate, and we've done this earlier, where we said that RT is equal to 1 plus R1 multiplied by 1 plus F11 multiplied by 1 plus F21 all the way up to the forward of 4-1. So we've already seen that before, that we can get any rate, any current maturity rate on a spot curve by just multiplying all of the individual forward rates forward. Well, that's what this is saying. Do you believe that? Probably not. There are not many that do believe that. So that's why we move to something called local expectations. So local expectations has the same implication as the pure expectations or the unbiased expectations, except that it restricts the range over which that's valid. It says that the expected return for all bonds is the risk-free rate over short time periods only. The expected return for all bonds is the risk-free rate over short time periods only. So for example, if you have a 6-month horizon, the 5-year, the 12-year, the 30-year are all equal. If you buy them and sell all of them after 6 months, your expected return will be equal. And the rationale behind that follows like this. If we're at time 0, and let's say this is the 1-period spot rate right here, this is the 2-period spot rate, this is the forward rate. If you do not believe that the forward rate is an unbiased estimate of what the next term spot rate will be, you cannot argue that the spot rate is the spot rate. That is the spot rate. So as long as your holding period corresponds with the existence of that spot rate and doesn't fall into a need to roll over into the next rate, in other words, your investment horizon is not dependent on whether or not this forward rate becomes the next spot rate, then it doesn't matter what bond you hold. In other words, your expectation is local as opposed to global in the curve, which is why it's called local expectations. Do you believe that? Do you believe that if I held a 2-year, a 5-year, a 12-year, and a 30-year bond over just one period of time and then sold those that my expected return should be equal on all of them. Well, if you find that this theory has value, you would tend to believe that. Does the evidence suggest that's true? No, it doesn't. So before we leave the pure expectations and local expectations and move on to the next three theories that we'll look at, understand what we're trying to do. We're looking at the shape of the yield curve and we're saying, why should it look like that as opposed to anything else? Why should it look like that? There must be some theory, some reason why a curve takes on the shape that it takes on. We tried to argue that, well, because in an efficient market, traders will recognize whether the forward rate is too high to represent what a future spot rate would be and will trade it away. And we thought, well, that doesn't make a lot of sense because the conclusion doesn't seem proper, that if we hold any bond, we should get the same return, that we're indifferent between them. But we know that that is not true. So what's going on there? Well, we have to understand why the forward curve is not an unbiased predictor, that it is a biased predictor, not an unbiased predictor. When we move out in terms of maturity, there'll be a maturity risk premium built into the spot curve. It is built into these prices. If the forward curve is derived off of the spot curve, and the spot curve is reflecting more risk than just the risk-free rate, if it's representing risk in terms of maturity risk premium, that premium will be imported into the forward curve. If it's imported into the forward curve, how can you say that an expected future short-term spot rate should have a maturity risk premium? It shouldn't. So, but if it gets imported into the forward curve, it will eventually show up, or an expectation that that will be the future spot rate. So, it ends up being that the forward curve is typically biased upwards. So let's have a look at what we have. The maturity risk premium is most likely in the spot curve. Therefore, forward rates would absorb this premium and hence would then reflect a maturity risk premium in the expected future spot price. Now, local expectations avoids importing MRP because it doesn't use any forward rates. It just says if you're holding it over the one period spot rate, you're good. So the spot rate doesn't have that premium in. It avoids using anything on the forward curve, so it avoids importing unbiased expectations. So it doesn't. It avoids importing the maturity risk premium or other risk premiums into short rates. Any excess risk premium would be arbed away in the one period spot rate. So if there was excess premium in the one period spot rate, it would be arbed away, thereby being a true risk-free measure. But we can't say that about the forward curve. The forward curve is derived off a spot curve, and if the long end of the spot curve includes premiums for risks other than default risk, that will get imported into the forward curve. So that the shape of the curve reflects more than expectations. The shape of the forward curve does reflect future expectations, but it also reflects premium that was sitting in the long end of the curve that, because these are implied rates, got imported in. Okay, our second one, liquidity preference theory. This is kind of like the expectations theory in a way, and it's kind of like local expectations, which I just described. What this is saying is that at the long end of the curve, some liquidity premiums exist, and that they increase with maturity. Therefore, even with an expectation of unchanging short-term spot rates, what does that mean? If we have an expectation of unchanging short-term spot rates, it means we have a flat forward curve. And if we have a flat forward curve, and if the forward curve is derived from the spot curve, and the spot curve can be derived from the forward curve, we would have a flat curve altogether. So that even with an expectation, even if the market expects unchanging short-term spot rates, which would imply a flat forward curve under unbiased expectations, the yield curve would still be upward sloping. Why? Because even if we expect the short rate to be constant over time, Under unbiased expectations, it would imply a flat curve. Liquidity premiums still exist and exist with maturity. So we can expect if we have a rate, let's say F41, there's an expectation that within 4 periods that'll be the spot rate. Some component of the expected spot rate will be in there, but the forward price will also reflect some of this liquidity premium that exists, and the further out you go, the bigger it is. So that the forward curve doesn't just reflect expectation of future rates, it has a whole bunch of other stuff in it. So that's kind of like local expectations. Local expectation says that the only really good rate you can use is the 1 period spot rate, because it doesn't have anything in it. Any extra premium would be arbed away. Liquidity preference theory is just avoiding that altogether and saying, yeah, that is the case. That is the fact. You can still have an upward sloping yield curve. That does not mean that there's any information in the upward sloping forward curve about what future expected spot prices will be. So let me be clear on that. Liquidity preference theory is saying that you can still have an upward sloping spot curve, which would result in an upward sloping forward curve, but that upward slope does not have any information about what the future expected spot price will be, because even if we assume unchanging short-term spot rates, the existence of the liquidity premium at the long end would still create an upward sloping yield curve. The next one is the segmented markets theory, which pretty much says there's no information, there's no real useful information in the forward curve that you can use. And what it does is it takes the spot curve and it breaks it into segments, different market segments, and it says, look, you got some players out there that cannot buy long-term bonds. They're not even in the market for long-term bonds. So even if they were mispriced, they're not going to do anything about it because they can't. So if there are more players in the market that cannot touch long-term bonds, that only have to deal with money market funds, then there'll be a different supply and demand fundamental here than there would be here. There'd be a different supply and demand fundamental to hit equilibrium in this market, and in this market, and in this market, etc. So that the shape of the yield curve represents the supply and demand fundamentals in those particular segments only. That while there are some players that can play the whole curve, the majority of each segment of the curve is dominated by those who only play that segment of the curve. Hence, the prices in those segments of the curve reflect the supply and demand fundamentals of those big players only. So that the forward curve derived off the spot curve isn't really reflecting expectations of what the future of this market will look like. It's really just noise. So, forward yields are not a reflection of expected spot rates or liquidity premiums. Hence, there's nothing in there. It's just if you like this idea, you would say the forward curve to me is useless. So each matching segment can be thought of as a segmented market in which yields are determined independently from yields in other maturity segments. So if they're independent and not dependent, you can't imply a forward curve of independently derived rates. Market participants are unwilling or unable to invest in anything other than securities of their preferred maturity. So if I'm a money market fund, I am unable to invest long. If I am a pension fund or an insurance company, I am unwilling to invest short. Do you believe that? Now, again, it's a theory that's trying to attempt to explain the shape of the curve, and we see that with pure expectations, the data doesn't support it. With local expectations, the data doesn't seem to support it. And while liquidity premium sounds interesting, it's the same problem with local expectations. The data doesn't quite support it. So if the data doesn't support it, then you need another explanation. This is another explanation saying, look, the data doesn't support it because there's nothing to support. There's nothing in the forward curve. Let's just say that, and let's have a theory that tells us that that's the case. And this is a theory that says, look, with this theory, the forward curve is crap. So any measure you'd get off it would not be supported by the data. There, I've explained all the anomalies by agreeing that the anomalies are actually the more common thing. So, what do you think? Let's move on to one more. This one here takes the market segmented theory and brings it one step further and relaxes some of the restrictions, especially the unwilling and unable part of being able to trade in other segments. Borrowers and lenders have a preference for particular maturities. I don't think that's uncontroversial. I think that's a good statement. Yes, borrowers and lenders have a preference for particular maturities. But that yields at different maturities are not determined independently. So now we're bringing the forward curve back in, saying, come on back in, forward curve. It looks like you have some role to play after all. So what they're saying here is that there are players in the market that prefer to trade at particular parts of the curve. But just because they prefer to trade at particular parts of the curve doesn't mean that rates are set independently along the curve. How is this so? Well, it combines the best of expectations theory and segmented markets theory together. So it brings in expectation theory because it allows us to bring that forward curve back in and say there's something useful there. It brings in segmented markets theory because there is something about money market funds not being able to trade long bonds. There is something about pension funds preferring not to trade short. There's something there. So can we combine them? And this is preferred habitat. If returns are compelling in other maturities, preferences will follow. So I may prefer to play at the short end of the curve, but if I see some wicked mispricing at the long end where I go, oh, come on. I mean, that's just begging to be fixed. There's an opportunity here. I'll do it. So that I prefer over here, I prefer this range, but I don't mind dipping my toe in the deep water if it makes sense. So suddenly, if there is something in the curve that does that's not dependent on other parts of the curve, there's arbitrage opportunity. I'll do it because there's money on the ground. I'm going to pick it up. So now the spot curve the rates along the spot curve are not independent per segment, but are dependent along it. Suddenly the forward curve has meaning again. Which one do you like? And you're going to have some idea of what you like, because you're going to come across some analysts who find that there's lots of information in here, and they'll base their forecasts on that information, whereas you might say, well, look, here's the fundamental flaw in your argument, is you're expecting future short-term spot rates to be what's reflected in the forward curve, and that simply just doesn't work. The forward curve doesn't have that kind of information. But if one person may believe that it does, and you may believe that it doesn't, well, what does that make? That makes a market. If everyone believed the same thing, there'd be no market. Everyone would be wanting to do the same thing, there'd be no one on the other side. So now you have a market, now you have opinions, but it's a matter of, can you justify your beliefs? If you believe the forward curve has value, you're going to need something to justify that, and you're going to need a theory of why the spot curve is shaped the way it is. If it's shaped according to preferred habitat or expectations theory, then the forward curve has value. There's information in there, we can use it. If you don't believe that, then you would think there's no information in that, I'm not even going to use it. So we're going to move on now to sort of a related discussion of what we just left. We just left a discussion about the theories of the shape of the yield curve and why it looks the way it looks. Because if we're going to forecast what it's going to look like 1, 2, 3, 4 periods from now, well, we need some theory that drives our thinking about what is going to change. What would change it? Well, we don't know what would change it unless we have a theory of how it's constructed to begin with. The modern term structure models do this quantitatively. So they are quantitative descriptions of how interest rates evolve over time. So they're models. Well, whenever we have a model, we know it's a simplification of reality. We accept that. We accept that simplification to get some kind of explanatory power to make things simple. But we're going to need some things. And typically we need two things when we have a model. We need some inputs to the model. Those are called factors or independent variables. So we need factors, and we're going to look at several different models that work either with one factor or multiple factors. And we need some parameters for the model, and in these parameters we build in our assumptions about how they will behave. So let's look at two categories. We'll look at equilibrium term structure models and arbitrage-free structure models. A warning up front, well, not a warning, a limitation. Notice that the learning objective says describe, to describe. It's very hard to describe these abstractly without showing you the model itself, the variables and the parameters of the model, and looking at the model and describing the model. Once you describe the model, you can describe what's going on, but to describe it abstractly is very difficult. To go beyond that, we would be wading very deep, well, maybe not deep, but chest high for sure. We'd be wading chest high into PhD waters. I don't think we want to do that. The goal here isn't to turn you into PhD candidates, it's to turn you into analysts. So let's keep that in mind, that I'm going to hold back. Upon introducing the model, I'm really not going to go much further than that because you don't really need to. You just need enough to describe the model and what's going on. We're going to introduce two models in equilibrium term structure and one in arbitrage free. These are just these are just three models of many that are out there. As a PhD, as a finance PhD who's seeking tenure, some of the easier papers to write would be, well, let's do a 2 or 3 factor model to explain the shape of the term structure, and I'll grab data from a particular period of time and I'll introduce some factors that I think are relevant. I'll test it, and if it fits nicely, there's my paper. I got a paper. So there are plenty of models out there. There are plenty to choose from. In fact, you may even create your own someday. But we'll just show you the general structure of what these term structure models really try to accomplish, all right? So there we go. So equilibrium term structure models, what do? They describe term structure dynamics. So we're looking to describe change over time. That's bringing the word dynamics. We're not looking to explain a shape. We're looking to explain the evolution of the shape over time, using fundamental economic variables that are assumed to affect interest rates. Our models will require us to model two components of change. One is a drift term. And a drift term is if we expect a rate to go from a low rate to a high rate, we have to get it there somehow. So we need some way to drift it there. And an assumption about volatility, because it's not going to go in a straight line. There's going to be some movement that looks like this. So we need to be able to explain the evolution of a yield curve over time that accounts for, hey, you know what, stuff happens. There's a stochastic term on there for, you know, what happens, right? And of course there's a drift term in there, and we need an assumption about, well, what are we assuming when we say the drift term, and what are we assuming about volatility, right? So we can have one factor or multi-factor models. We're going to look at two one-factor models in this category, in this family, the equilibrium term structure. Then we'll look at a multi-factor model later. We have to make assumptions about the behavior of the factors, and the model should be parsimonious. By this, we mean, look, you can always explain the world if you include every single variable that ever is. Just you'd never be able to collect all the data on that at any given time. You couldn't work with it. So we simplify. So you may look at these models and say, you can't explain things with one or two variables. No, you can't. That's not the point. The point is, does it do a good job? And if it does a good job, that's good enough. All right, the first model we'll look at is the Cox-Ingersoll-Ross models, the CIR model. And let's just go right to the model, and then we'll talk about it after. It looks like this. I know it looks kind of complicated. What do all these things mean? But once I describe all of these terms, you'll pretty much be able to see exactly what's going on here. So let's have a look. DR, what is this? This is our dependent variable of the model, and it is a change in the short-term rate. So this will tell us what the change in the short-term rate is as a function of all these things. This first component, from A all the way to the T, everything in here, is the deterministic part of the model. This is the stochastic part of the model. So let's deal with the deterministic part. What have we got? We've got R. That is our observable short-term rate. That's our input. That's our factor, the short-term rate. This is a one-factor model. It says up here a single factor, the short-term interest rate. There it is right there in the model. What is B? B is a long-run value of the short-term rate. It's the long-run value. So why do we have B minus R here? because we're assuming mean reversion. So that if the short-term rate is below the long-term rate, this term in here will be positive. If the short-term rate is above the long-term rate, this term in here will be negative. So if it's negative, we can see that we're going to have a negative term here pulling the rate down towards its mean. If it's positive, it means the short-term rate is below the long-term rate. This first term will be positive, pulling the interest rate up towards its long-term mean. So that captures mean reversion. The A, what is that? That is the speed of mean reversion. So we're going to need an assumption about what the long-term value of the short-term rate is. We're going to need some assumption about the speed at which mean reversion happens. And this second part here is our stochastic part. We have sigma, the square root of r, the square root of the short-term rate. This captures volatility. And our volatility variable is distributed as normal variable, mean 1, standard deviation is 0, so it's a standardized variable. And the assumption here, because of this square root term in here, if you think about this, it's basically saying that volatility increases as rates increase. So at low level of rates, volatility will be low. At high levels of rates, volatility will increase. So you don't have constant volatility across different levels for the rate. Keep that in mind. You don't have constant volatility. So let's have a look. Let's map that out and let's see what happens. So if rates are low, we'll start at a low rate and we'll find a nice color to use here. Why don't we use orange? Okay, so let's just follow this through and see what we have. We'll start with our short-term rate right here below our long-term rate. This will make the term in the brackets positive. A will be positive because it's the speed of mean reversion. You can't have negative speed. And dt over here means for a very small change in time. So what we do is whatever our change in the short-term rate will be, then becomes our new short-term rate, and then we move time forward by 1. And then we'll get a change in the short-term rate, which then becomes the input for the next period of time. So when you run this model, you can run it over 80 periods of time or over 100 periods of time and watch the short-term rate evolve at each turn. So this term will be positive, and here we have a low rate of r, so volatility will be low. So as we move towards a short-term rate, we'll see short-term rates moving around, but as the rates start increasing, volatility starts increasing. So as rates get really high, our volatility on the interest rates increases, and as we start pulling down towards the mean, volatility will drop, etc. So you can see what I'm doing here is that I'm showing that volatility in the rate has increased up here, but volatility down here is low. That's what this is mapping, non-constant volatility across time, so that across levels. So as the level of the short-term rate increases, its volatility tends to increase as well. That's an important distinction of this model versus the next model we do, takes that out and says there's constant volatility. So if we were looking at this in terms of how this plays out for our curve, as the rate here is changing over time, and this is periods of time in the future, we would tend to it will give us a forward curve. And from this forward curve, we can then derive the spot curve, because we will know, and they have the same period here, we will know how to get the spot curve from the forward curve, because remember now we're moving, the model is allowing us to move forward in time. So as we move forward in time, this is telling us what the short rate will be at a period in time. So that will plot out our forward curve. We'll write this here. That'll plot out our forward curve. And from our forward curve, we know that we can derive the spot curve. So that if the model that we choose, we'll choose a 10-year period of time, and we'll calibrate our model according to that period of time. And then we will use some forecast for the next period and start our model to predict where we think, or what we think the forward curve will look like. And from that we can derive a spot curve. So the second model we'll look at is really the same thing that we just looked at with one change of assumption. This is a Vasicek model. You have the same deterministic part, except look here, we don't have the square root of r. It assumes constant volatility at all levels of the interest rate. It assumes constant volatility. So if we're looking at both the models, they're both mean reverting, which is nice. They both have short-term rate as the single factor. They differ in their volatility assumption. So which one do you want to use? Well, you're going to have some assumption about future volatility. If you believe that volatility is going to be fairly constant at all levels over the next how many periods that you want to forecast, you will use a Vasicek model. If you anticipate that, no, well, as rates start going up, I do believe volatility will increase, then you would use a CIR model. Not very good at modeling observed term structures, though. It sounds nice, doesn't it? It really sounds nice. But when you input, if you go back, if you take a 10-year period of time and you say, well, here's the rate at the beginning of time. Let's put this short-term rate in. Let's draw out what actually happened to short rates over that 10-year period of time. Now let's model derive it and see if we get the same thing. Not really. Not really. It doesn't really give the same thing, because you're using that 10-year period of time. You'll start with the input of the short rate and you'll model it. It doesn't look like it. You might tweak your assumptions. Well, maybe the drift component's a little slower, a little faster. Maybe volatility isn't where we think it is. Let's try this. And you'll try to replicate in history. You'll use your 10-year period and you'll try to replicate it. If the model replicates what exactly happened, great. That has some predictive power. But if you can't replicate history, then what makes you think that the model will be any good at telling you what will happen if it can't even tell you what did happen? So here's the deal with this model. Rather than saying that the model is deficient, this is beautiful, you're going to love this. Rather than saying that the model is deficient, it's saying, look, if our model doesn't replicate history very well, it's because history was full of mispricing. If history were efficient, if there wasn't any mispricing, it would look like our model. So it's not that our model doesn't look like history, it's that history refuses to look like our model. So our model, when it's off, it assumes mispricing. Okay, let's move on to an arbitrage-free model, or the family of arbitrage-free models. We'll only look at one, the Ho-Lee model. This is called a partial equilibrium model, as opposed to the previous family you saw, which was called the equilibrium term structure model, more of a general equilibrium term structure model. This is partial. We begin with the observed market prices of a reference set of rates, a reference set. So you're not just going to have one rate, you're going to have a reference set of rates. Or financial instruments. They don't have to be rates. You might look at the prices of financial instruments and from that derive the rates. But either way, you'll end up with a set of rates. And let's say you end up with 10 rates. And you make the assumption that they are priced correctly. Remember, the last model's problem was that it made the assumption that if the real world doesn't look like our model, the real world is priced incorrectly. Well, here in the Ho-Lee model, it says, well, let's just say, look, let's start with the assumption that the market is priced right. And rather than deriving the curve, let's just take the real prices in the market as given and use those. So the model is then calibrated so that it generates the observed reference rates. In other words, they create the model that can perfectly, well, not perfectly, but does that comes as close to describing what really happened as possible. And their thinking is, look, if we have a model that can describe the past as it happened, we can project it forward. We'll just assume those prices are correct and we'll use those in the model. Hence, that's why it's called arb-free, because they assume they're correct to begin with. Does not attempt to explain the yield curve, though. It doesn't try to explain why the yield curve is shaped the way it is. That's not the idea of the model. These quantitative models, that's not their purpose. Those were the theories. The theories of the term structure attempted to explain the shapes. These models take the shape as given. That's it. All they do is they say, look, who cares how or what theory you have in mind? We're going to take the shape as given. All we want to do is project it forward based on the quantitative data that we have on its history. Now, if you think about equities and you think about fundamental analysis, basically fundamental analysis is really a theory of what moves stock prices, isn't it? The price earnings, return on equity, the retention ratio, are we growing, are we not? Do we have residual income, free cash flow? These are all theories about what adds value to the firm. But if we want to do something where we just take it as given, and we say, whatever, the price in the marketplace is the price, let's start there, and let's look at the past and see if we can project the future out from the past. That sort of sounds like technical analysis, doesn't it? So if you got the feeling over this learning objective that you thought, this sounds a little more technical than it does fundamental, you're right. These are very technical. Basically, you're just looking at the pattern of the change in the yield curve over time. You're picking out some factors or some variables that you think explain it and projecting it forward. In technical analysis, what are the factors we think explain things? Volume and price. Volume and price, and not just volume and price, but the length and the size of the movements. So this is more technical than it would be fundamental. So we are coming to the end of this rather long chapter. And the last two learning objectives, I think, tie this chapter together very nicely by ending on a note of, okay, so what? What do we do about all that stuff? And we've moved from attempts to explain the shape of the yield curve. You'll recall we had local expectations, liquidity preference, segmented markets, preferred habitat. All of those were attempting to explain why a yield curve adopts a particular type of shape. We moved from explaining to describing the yield curve with some models. We looked at a CIR model, a Lasicek, and a Holy model, which didn't really try to explain the shape of the curve, but just to describe the shape of the curve. So now we're going to move to a way to measure the risk of a changing curve. Rather than just explaining the shape of the curve or describing the shape of the curve, we're going to say, all right, so I have a forecast of what I think the yield curve will look like in a year. I'm going to position myself for that. So that's the risk we want to expose ourselves to. But there's risk we don't want, which is the unanticipated move in the yield curve that we didn't anticipate, that we're not positioned for. So these last two learning objectives really focus on that, saying, okay, great. You've got enough information now that you know how to base a forecast on where the yield curve will go. You have some justification for why you think the yield curve will take on the shape it does. You know how the change in the spot curve will affect the forward curve, so you'll know how to determine an expected future value for a bond based on what you think is going to happen. What if things go wrong? That's called shaping risk. And shaping risk is the sensitivity of a bond's price to the changing shape of the yield curve. Now, again, let's stress, you are going to position yourself for a changing shape of the yield curve, or you may say it will not change and you'll position yourself for that. But how sensitive will your portfolio be to changes in that curve that you do not anticipate? You have to be able to measure that risk and then hopefully do something about it. So, for active bond management, trades are based on a forecasted yield curve shape. And you need to hedge yield curve risk on a bond portfolio. So you want to be aware, you want to measure that risk and determine what you do for those two particular reasons, to base your trades on what you think you're going to forecast and to protect yourself from what you did not forecast. So the question now becomes, great, we have an explanation of the yield curve, and I'll choose one of the four, or maybe a combination of them that helps me explain yield curves. That'll set up the basis, the ideology on which I'll forecast what the future will look like. But what will cause the yield curve to change shape? All of the variables that will cause it, I can't track them all. Is there a way to come up with a number of variables, a small number of variables that, look, pay attention to these variables because these are the ones that are going to change the shape of the curve, and if we can quantify those variables, we might be able to hedge out the risk of that happening. Well, it turns out that's what yield curve factor models do. And the more popular one that is from 1991, Litterman and Shankman. Litterman was at the time a VP at Goldman Sachs, VP of Research, Fixed Income Research, and Shankman was at the University of Chicago. So I like that combination because you have an academic and a practitioner. And the practitioner brings a sort of a big so what to research by saying, look, you can't do research for research's sake. There's got to be a big so what. It's got to matter to us. It's got to be usable and practical. So I like it when practitioners and academics collaborate on papers. So I'm interested in seeing what they have to say. I'm more interested in this than if they were both two academics. Well, they have a three-factor model. And the three factors that they identify are level, steepness, and curvature. But this is a very interesting model in that they can claim that these three factors are independent of the others, independent of each other. What does that mean? That means if you model the yield curve, the sensitivity of pricing using just one factor level, and then you add steepness, the addition of steepness will not take away explanatory power from level. It adds explanatory power. They're all independent factors. So how do we know they're independent? Well, it's the process that they used. And they used a very particular process in which they ended the process by naming the factors. Typically, your research will start by hypothesizing that certain factors have an effect. You'll already have the name of those factors, and then you will test it. And in testing it, you will look at your data set and start removing things that challenge your beliefs so that in the end the data set tells you exactly what you want. In this particular process, they started the other way around and said, well, we don't know what we're looking for. What does the data say? Let's have a look at that process. So what they did was they started by taking 10 key rates, and these are just points along the yield curve, different points of maturity along the yield curve, 10 different maturity points, and developed a variance-covariance matrix, a historical variance-covariance matrix among all those rates, so that as short rates move and midterm rates move and long-term rates move, do they tend to move together in opposite directions? How do they co-vary? And from that, they say, okay, look, we have this. Now, let's say we had a factor that explained that. How much could it explain? If we did have one, how much could it explain? In other words, how much of this covariance among all of the 10 key rates seems to be related? And they extract that out, or the data, the statistical package software used extracts that out and calls that factor 1. Factor 1 doesn't have a name. What the statistics is telling you at that point is saying, hey, look, Mr. Researcher, here's a factor that if you had a name for this factor explains the majority, well, I shouldn't say the majority, the first factor that's extracted has the largest amount of explanatory power. Each factor you extract after has less and less explanatory power. But it says, look, if you can name this, it's a factor. So what you need to do after you extract the factor is look at the effect it has and then try to figure out, well, what could it possibly be? So we try to extract independent factors that explain the variance-covariance matrix. That's called principal component analysis. And the idea behind principal component analysis is that it looks for what are called orthogonal factors. And an orthogonal factor means that each factor is statistically independent of the next one. So it'll make a pass of the data set and extract a component that accounts for the largest amount of the variability. Then it'll make a second pass and extract variability, but it cannot use any of the variability from the first pass. It can only use what's left over. And that will get the second amount, or the second highest amount of variability, and on up to a maximum of 10 factors, because we only have 10 maturity points. You can't have 11 factors explaining 10 things. And that's it. Typically, the first 1, 2, maybe 3 pretty much tell everything. And you can add the explanatory power of each factor together because they are linearly uncorrelated. So we would use principal components analysis typically for exploratory data analysis. You have a data set, you know something is there's some variance in there, but you really don't know what you're looking for. Step one is to say, well, are there any real factors in here? And if the data set comes back saying no, well, then you're done with that. But if it comes out and it pulls out one or two really big ones that explain the majority, you say, aha, something's going on. What are those two things? And that's exactly how this thing works. Okay, so let's look at the job they had after the statistics were done, and they saw that they had three factors. The first factor. Now, keep in mind the name. It's called level. They called it level, but they didn't. It has no name when it's first extracted. It has no name. You have to figure out, well, what could possibly be causing that effect. So they look at the effect of the first factor, and how do they do that? They change the first factor one standard deviation up and one standard deviation down, and have a look at the effect across the maturities. So they'll plot maturity versus the change in yield for the different maturities, and then they'll change the first factor and see what happens to the yield. They'll change it up by one standard deviation, they'll move it down by one standard deviation, and see what happens to the yield. So for the first factor, when they increase it by one standard deviation, the yield across all maturities goes up in the same, it moves in the same direction and almost at the same proportion across. It's not like it's, if you look at the other two, it doesn't display that. And when they move it one standard deviation down, it ends up moving all negative and pretty much around the same range. So they said, you know what that looks like? That looks like just a level change in rates. It looks like a parallel shift of the yield curve. So they said that must be what it is, because lots of factor models that try to describe the shape of the yield curve use short-term interest rate as their input. Remember the models we did? The CIR model and the Vasicek model used short-term inputs as the rate. So they said it must be a change in rates. Well, go back to level one. This is what we've done. We looked at the sensitivity of a bond or a sensitivity of a bond portfolio to a change in rates. But we assumed a parallel shift of the yield curve, right? So this is duration. We can capture this with duration. So for the first factor, we probably could have guessed that right away. Duration. Responses, you notice here, the responses in the same direction by the similar magnitude, so they call that a level. Here's the next factor. The next factor, when they changed the standard deviation by 1 up and by 1 down, they observe the effect it has on the yields across the maturity. So for a 1 standard deviation move upwards, this is what they noticed. Well, when we move this factor, which we don't know what to call it yet, by 1 standard deviation, we notice that yields on the short end of the curve drop, but yields on the upper end of the curve tend to increase and then sort of taper off at the end. And then when they did it the other way, they noticed the reverse of that yields at the short end tend to increase and yields at the long end tend to decrease. And they said, well, what we have here, that's a terrible color, let me get a better one. What we have here, it seems like, is if the yield curve looks like this and then suddenly changes to this, well, what happens here is the short rates tend to drop and the long rates tend to increase, and that looks like what's going on here. Well, that's the steepness, that's the slope of the yield curve, going from a flat yield curve to a steeper yield curve. So they called it steepness. Now, it's important to understand this. These factors were developed without any manipulation of the data set. It was the honest representation of the variance and covariance in the data set, and then they named them after the fact. So they called this one steepness. The last one ended up having this effect, or if it was a negative standard deviation move, it would be the other way around. So they look at this and they say, well, what could possibly cause that? Now, I want you to, we know it's called curvature. We know they ended up calling it curvature, but imagine that you didn't know that it was called curvature, just to give you an idea of how difficult this can be. You didn't know it was called curvature. You're given this and you're saying, there's an effect that has this result, that when this particular factor moves by 1 standard deviation, this is the result we get. Short rates drop Midterm rates look like they rise a bit but then fall, but long-term rates are falling again. So you got a short end of the curve that drops, the middle end of the curve rises, and the long end of the curve drops. And then if it's the other way around, it's the other way. The long and the short end of the curve rise while the middle curve either stays the same or drops. What do you think that is? Now, again, you don't know what's called curvature, and you have to figure out, well, what effect could that be? Well, it turns out that one of the researchers, I don't know which one it was, said, you know what? I've done research before on a particular variable, and this looks like the same thing. So he concluded the results display the same pattern as the impact of interest rate volatility on the shape of the curve. So they call this factor curvature, which really is capturing the volatility across the rates. Kind of a neat thing, isn't it? That you start with the data and then you end with your factors, as opposed to most research which starts with hypothesized factors, then goes to the data, and guess what? If the data set's not being a cooperative, you torture that thing. Get rid of this one, get rid of that, relabel this, transform that. Oh, look at this. Hey, there it is. There it is right there. As soon as I moved around 20 different rocks and dug a few holes, I found it. Whereas this just says, here's the landscape. What do you think caused the landscape? So before we go, let's talk about yield curve volatility, because we did bring it up in the last learning objective as a very close relationship with curvature. So how can we get an idea of what volatility looks like? And one of the things that we're going to do is look at volatility at each maturity. Because the first question with volatility, is it constant across all maturities? Well, the answer to that is no, but what does the shape of that look like? And when we plot maturity, and you can see maturity here along the horizontal, you can see volatility on the vertical. When you plot volatility for each maturity, you get a downward sloping curve like this. This, it should be no surprise, is called a term structure, but it's a term structure of interest rate volatility. It is the yield the yield volatility for a zero coupon bond at each maturity. So have a look at what the results look like, and this is taken before 2008. It doesn't include 2008 so that it keeps out that really extraordinary volatility that occurred. But we get to sort of results that look like this, which is consistent with this type of curve, that if you look at the short end of the curve, look at the measures for volatility, and notice that they drop pretty consistently, well, fairly consistently, you'd say monotonically, they drop right through to the 30-year. That each, as you go out longer, volatility continues to drop, so it's not humped in any particular way. And what we've been able to find, or what practice and research has been able to find, is that the volatility at the low end of the curve, it is more volatile than the the short end of the curve is more volatile than the long end of the curve, but that this volatility is more strongly linked to uncertainty about monetary policy, and that seems to make sense. Before any central bank meeting, there's always some anticipation of something that's reflected in rates, and when the announcement is made, either it is or it isn't the way it's supposed to be, so that whatever was priced in gets taken out, whatever wasn't priced in gets put in, so there's a lot of volatility at the short end. Whereas the longer end of the curve is more strongly linked, or volatility I should say at the longer end of the curve, is more strongly linked to uncertainty regarding the real economy and inflation. So that wraps up this chapter. Now, if you're looking at the reading, you might say, wait a minute, there's a little bit more left here. Shouldn't we be worried about that? It's a walkthrough example leading through different measures of yield curve risk. The first one we've seen in level 1 is duration. The second one we've seen as well is measuring key rate duration. This is for a non-parallel shift in the curve. And then the third one sort of says, well, let's decompose the idea of level steepness and curvature and measure that effect. Well, while that's an interesting exercise, it's not good enough to really get an idea of what's going on. And the big thing, you don't need it. It's not required. It's just one extra step there if you want to see how it plays out. But it's not laid out very well. It's difficult to follow. You're not quite sure what point they're trying to make, and I'm not quite sure what point they're trying to make. If they wanted to make a point, they would have drawn out a much better example with a little more detail and shown the process far more clear. That they didn't do that means, hey, look, this is a kind of an interesting thing to look at. But listen, for the learning objectives, we are done. You don't need that. If you're interested, go ahead and read it, but you don't need it.